Good evening, everyone. Welcome to the Center of the Universe Star Party for November 20th, 2021. My name's Aaron. I'm going to be your host for the evening, and I've got a great night for you. Our feature speaker is going to be talking about or speakers, I should say, are going to be talking about the James Webb Space Telescope. So I'm super excited about that. First off, though, I'd like to acknowledge with respect the Sinchothan speaking peoples on whose traditional territory the observatory stands and on whose traditional territory we live, work, and play. We share with these peoples historical relationships with the night sky. If you're joining us on YouTube tonight, we would love it if you would like and subscribe. That helps us find new people and get this content out to more people around the world. You can also find us on all the social medias at FriendsDAO. If you'd like to help support us, you can find out a whole bunch of ways to do that on our website, centeroftheuniverse.org. We're a membership-supported organization. So if you'd like to get involved, we'd love to have you. We are also looking for volunteers as we gear up the center to open to the public again, hopefully in the next few months. We're still waiting on some word from the NRC to do that, but we're prepping some new exhibits and trying to get folks trained on how to work inside the center. If you're with us on either YouTube or Zoom and you have any questions during this evening, please post them in the chats. We have some folks who are going to be watching out for questions, and we will bring those either to our presenters or to our Ask an Astronomer folks who will be on after our presenters. These questions can be anything related to the talks or just any curiosities you have about astronomy in general. So first on our list today is What's Up in the Sky with Don Moffat. That is, if we can see through the clouds, if the rain ever lets up. Don, over to you. Oh, Don, you're muted.
All right.
There we are.
Okay, sorry about that. So, hi everybody, and I'd like to tell you just a little bit about what's happening up in the sky at this time of the year. And let's just start around sunset, and we can see that Venus is over in the southwest part of the sky, shining brightly, and a little bit to its left we see fainter Saturn and then Jupiter, and of course they're on a line because of the plane of the solar system, so you would expect them all to be more or less lined up like that. And this is, we've just passed a lunar eclipse, and so of course a lot of you have already seen the beautiful photos of that online. And let me just move over to adjust the time a little bit, if I can, until later in the evening. And just, we can see that that Orion is actually starting to come up now in the southeastern part of the sky, and so we this is, and of course with Orion, what was a great interest in the last 20 months and so on was what was happening with the star Betelgeuse. And so this is a great time to start watching it to see if there's anything else that happens. And my understanding is it's now thought that it was large grain circumstellar dust that caused the dimming of it over a factor of over 2.5 times. And so we don't know if that's concluded. We don't know if that's going to reoccur, in other words, in the next little while. There are some meteor showers at this time of the year. There's actually one just starting, but it's not really something that is terribly noteworthy, and that's the Andromedids. And that's not something that one would normally hear much about. And it's a meteor shower that typically only produces about 8 meteors per hour. But one of my favorite meteor showers is the Geminids, which occurs on December 13th and 14th, and that's a very reliable one, weather permitting, because the meteors tend to be very slow moving. And as many of you know, the reason for that is because they're essentially catching up to the Earth, coming from behind as we're moving along in our orbit, and they're coming along in much the same direction. And so they hit the Earth's atmosphere at a slower speed. And so they move across the sky much slower than the Perseids, which we see in August. With the Perseids, I'm always a little frustrated because I missed half of them because I see them out of the corner of my eye and they're gone before I have a chance to turn my gaze properly. But with the Geminids, you do have that time typically, and so they're very enjoyable to watch that way and very colorful. So I think I'm doing a bit of an abbreviated what's up in the sky session tonight, but I do encourage you to get out there and enjoy these beautiful night skies. One thing else I can also just mention too is that the constellation Andromeda is visible essentially all night these nights, and you can look for the Andromeda galaxy, which is very visible, and so especially through binoculars, you can try your hand at finding that and seeing what you can see. Okay, so back to you, Aaron.
Thanks, Don. Yeah, I'm hoping I can get out and see the Andromeda galaxy, weather permitting. It's been a little cloudy and wet of late.
Yes.
BC.
Aaron, I'm just wanting to ask if there's anybody online who actually did see any part of the lunar eclipse, like a night and a half ago. I'm wondering if anybody did get out. I know that we had one of our young members, Nathan, did get up and got a couple of little shots through some clouds. But is there any, if you can put something in the chat, or you can maybe saw the Stephen just said he's out from Calgary. Stephen, can you put on your audio and let us know a little bit about it?
Yeah, I'm not sure what you want to hear. I set up about midnight, back in bed by 4:30. It was quite spectacular. It was a little bit cloudy, but it kind of provided a moon filter.
Yeah.
So
nice.
It wasn't too bright. I took lots of pictures with my iPhone and camera. Yeah, about 2:00-ish, I guess, the maximum eclipse, it turned very bright red, had a little diamond on the bottom left-hand corner. And by 4:00 it was all over. So yeah, it was quite nice.
Fantastic. Yeah. I'd heard bits and pieces of it. I didn't actually get out to see it, and I think most of BC was clouded over that evening, or at least the lower half of it.
But it was absolutely lovely by like 5:00 in the morning. Like if you were up at 5, it was a lovely clear sky, and I was going, that's not fair,
I was not up by 5.
Oh, okay. All right. Okay.
All right. So with that, let's move along to our feature speakers. We're lucky enough to have 2 speakers who are project scientists for James Webb observing programs. First off, we have Dr. Matt Taylor, who hails from the Comox Valley. He's a research astronomer at the Hertzberg Institute in Victoria. Will be taking up a faculty position at University of Calgary in 2022. Dr. Taylor's research is centered on how low-mass stellar systems like dwarf galaxies, globular clusters, and ultra-compact dwarfs can be used to constrain the formation and evolution of their giant galaxy hosts. Most recently, Matt is the principal investigator for a James Webb Space Telescope program designed to probe the motions of stars deep within their hosts and thus search for smoking gun evidence of any massive black holes lurking in their cores. Then we'll have Dr. Chris Willott, who's a senior research officer at the National Research Council's Dominion Astrophysical Observatory, the one right behind me. Dr. Willott started working on the James Webb in 2006 and is presently the Canadian James Webb Space Telescope project scientist and principal investigator of 2 different James Webb Cycle 1 observing programs. So with that, I'd like to welcome Dr. Matt and Dr. Chris.
Hi there. I'm here. I don't think Matt's here yet, but we agreed that I would speak first.
Sounds good.
So hopefully he'll turn up before I'm finished, and then we'll be good. So hi everyone. Nice to be able to talk to you tonight. A little bit sorry about my video quality is a little bit fuzzy because it's kind of dark now. I do most of my Zoom calls during the day when image quality is a little bit better. But anyway, you don't really want to see me anyway. You want to see my slides. So I'll get that going. So I'm going to talk to you today about the James Webb Space Telescope. Here's a picture of the telescope, an artist's impression, and we'll actually have it up in space flying pretty soon. So that's a very exciting time.
I don't think we have your screen shared yet.
Okay, that's a good point. I might need to do that. I'll start that.
You're right, Chris. We don't want to look at you.
Yeah. Okay, that's better. All right. Now you can see. Okay. I'll
I don't know if you want to. Yeah, there we
go. Okay, there we go. So here's a picture of the telescope. As was mentioned in the introduction, I've been working on this now for 15 years. It's a very long time since I went to my first meeting about this telescope. And work on the telescope has been happening in Victoria even longer than that. John Hutchings, who I'm sure many of you know, started working on this project in the late 1990s and was fundamental in getting getting the Canadian contribution approved so that Canada can take part in this mission. So here's a little picture of the telescope. So you probably, most of you are familiar with it vaguely, but just the main key points. We have the very large gold segmented mirror. There's 18 gold-coated mirror segments here, and the total diameter of the mirror is 6.5 meters. What you can't see behind the mirror here is the instrument module, which contains all the science instruments that I'll talk a bit about later. And then below the telescope here, you can see the grayish and then pinkish, large spread out area is the sun shield. And the sun shield is absolutely critical because this is what keeps the telescope cool. Basically, the telescope will always be on the other side of the sun shield from the sun. And so it'll, after we get out and head towards L2, the telescope will start cooling down. And that sun shield, which is about the size of a tennis court when it's fully deployed, like shown in the picture here, is going to basically protect the instrument and the telescope and keep them very cool. And that's essential because this is an infrared telescope. So here's an actual picture of the telescope, not an artist's impression this time. This is how it looked when it was at the factory in Los Angeles area before it got packed up and shipped off to the launch site. Here you can see that the mirrors are folded as they will be for launch. So the secondary mirror is folded into a vertical position here. You can see the struts there. And then the secondary mirror, you can see at the top of the picture, just above the primary mirror. And then the wings, there are two. The primary mirror has 18 segments, and there are 12 segments in the center that's called the core region. And then on either side, there are 3 mirror segments, and those are called the wings. And in order to fit inside the Ariane 5 rocket, we have to fold it up like this with both of the wings kind of folded back. And then you can also see the sun shield here. And if you look carefully in this picture, you'll see a few people wearing white suits. And that just really gives you an idea of the scale of this thing. So it wasn't too long ago that we shipped it from the Los Angeles area on this boat, the MN Calibri, and it got sent all the way down the west coast from California to the Panama Canal, through the Panama Canal, and then around to French Guiana. And the picture on the right-hand side here, if you look in the bottom region, you can see there's a convoy of vehicles, and one of the vehicles has a big white cylindrical container, and inside that container is the telescope. And then, so this is a view of the launch site in French Guiana called Kourou. And this is run by the French Space Agency and ESA. And then if you look on the left-hand side, this is what the telescope looks like when it came out of that special container that it was shipped in. And this is the so-called alligator view of the telescope. And this is similar to how it's going to be inside the rocket, where it's all folded up. So you can see the 3 primary mirror segments there of the wings. You can see the secondary mirror kind of folded over at the front of the picture on the right. And then the alligator teeth are in the purple color. Those are parts of the sun shield that have been folded right up. And so you can see how compact the telescope is now compared to what we had before the picture when it was in the factory in Los Angeles. So because it has to fit inside the Ariane 5 rocket, it has to be very folded up like this. And that obviously means that when we get up into space, we have to unfold it. So this is what we hope we'll be seeing on the 18th of December, which is the scheduled launch date. So we're hoping it goes on time then inside the Ariane 5. And on the left-hand side, you can see a schematic with the telescope as it is stowed inside the fairing of the rocket. So where is it going? Well, James Webb is actually going to go to the L2 point, or the second Lagrangian point. It's not going into low Earth orbit as Hubble is, because we want to observe in the infrared, and we need to have a very stable platform there where we can keep it pointing away from the sun the whole time. And so instead, we're going out to this point called L2, the second Lagrangian point. And L2 is special because it's further away from the sun than the Earth, but it takes exactly 1 year to go around the sun. Typically in the solar system, if you go further away from the Earth, then it takes longer to complete one revolution around to get back to where you started. It takes longer than the Earth's 1 year. But at the L2 is special because the added pull of the Earth, in addition to the sun, accelerates your orbit a little bit. So in fact, you go around in exactly 1 year. And that means that James Webb will never get further away from the Earth than it would otherwise. If you sent it further away, then it was going slower than the Earth, it would get out of sync with the Earth's orbit every year. So where is L2? Well, if the plot at the bottom here is showing you it's about 4 times further away than the moon. So that's where we're going. And then obviously once we get there, we're basically going to keep the sun shield pointing at the Earth and the sun the whole time. And the telescope is always going to be pointing in the other direction. So it won't, we'll never see sunlight and we'll never get hot. And that means that we can keep the telescope and all the instruments at an incredibly stable temperature. And that's really important for observing in the infrared. So here are some pictures of the deployments, what's going to happen after it's launched. You can see the sun shield starts to come out first, and then the sun shield, the membranes start to come out, and then these the side spreader bars come out, and that spreads the sun shield further out. You can see that one side going in now, the other side is going out. And then the sun shield is actually made up of 5 separate layers of material, and the temperature gets cooler as you progressively go through those layers from layer 1 to layer 5. So you can see now we're separating out the layers, and you want to have a little gap between all those layers, and the gap between all the layers will allow any radiation that kind of gets through the first layers to then escape along the side, and it's going to kind of zigzag its way out along the sun shield and then go sideways into space and not get near the telescope. And then the last thing we do for deployments is bringing the mirrors into position, first the secondary mirror and then the 2 wings. If you want to see in much more detail all the things that are going to happen during this process of deployments, which takes a few weeks after launch, then there's a very nice Explorer on the NASA's website. So you can Google NASA Webb Deployment Explorer and get a look at the details of all the different things that are going to happen. And there's also a really good video of, which may be the one that Dennis is going to show, showing what happens during the first 29 days after launch when all these deployments happen. So after launch, unfortunately, we're not going to get really nice, pretty pictures to show everyone right away. It's actually going to take quite a long time before we are ready to do science. So we have, first of all, you don't have to look at all the details on here, but this is basically a chart of 6 months during which, after launch, after which we'll be doing various things to get the telescope ready for science. So the deployments happen mostly in the first 20 days. We head off to L2, we get the sun shield out, we get all the mirrors out, and then we reach the orbit at L2 after about 30 days. And all that time, the telescope is cooling down, because as soon as we get the sun shield out, we're protecting the telescope from the sun, and the telescope will just start cooling because it's not subject to the sun's radiation anymore. So all that cooling happens, and the cooling actually continues for about 100 days. But the telescope gets down largely to about the right temperature after about 40 days. And then after that, we have to get the telescope phased up, because we have these 18 different mirrors, and those mirrors aren't forming a perfect surface when we launch. We have to move the mirrors into the right place after launch so that they act as one giant mirror. And that is actually going to take quite a long time to get that process done. So we start off where we have basically, we'll have a picture where there'll be 18, if we point at one bright star, there'll be 18 images of that star on the detector, basically one from each of the mirror segments. And then we have to adjust the mirror segments until we can move all those mirrors to align up so they're aligned to each other. And we have to basically then get everything aligned to the instruments. So all the instruments are in focus and the mirror is behaving exactly as it's designed to do. So that's going to take quite a long time. We're looking at that process lasting until around about 4 months after launch. At that point, the telescope is finished, it's aligned, and then we have 2 months of science instrument commissioning. So this is where we have to get the 4 science instruments ready to be able to carry out science. So we have initial calibrations. We have to make sure that we understand the pointing. We understand exactly how well all the components are working compared to what was tested on the ground. So for the team that's working on this, it's going to be actually a very busy time during all of this, but especially for people like me working on the science instruments, it's going to be very busy during the science instrument commissioning phase, where we're getting a lot of data and seeing how the telescope's actually operating in space. So at the end of the 6 months, we should be done. And at that point, we will take some pictures of some interesting targets, and there'll be a big press release showing the world what James Webb can do. And then straight after that, we'll move straight into the first cycle of science and all the science observations that have been planned already. So why are we observing with an infrared telescope? There's a couple of main reasons. One of them is dust. There's a picture there of the Milky Way, and you can see the dark dust lanes in the Milky Way that you've probably seen if you're out at a dark site. But if you observe these kind of features with an infrared telescope, so here's a picture of M51, where the picture on the left is the visible and the picture on the right is the infrared. You can see all the dust lanes in the spiral arms on the left-hand picture are actually the regions of brightest emission in the infrared. So that all that dust that absorbs ultraviolet light re-emits it in the infrared. And so with the infrared, you can see right into all these dusty regions. And the dusty regions are very interesting because they're regions where stars are forming, planets are forming, a lot of the action in the universe is happening. So this is why, one of the reasons why we want an infrared telescope. Another reason is because of redshift. At the top hit of this plot, you can see there's a spectrum of a galaxy, which has emission in the ultraviolet, visible, and the infrared in the rest frame wavelength. However, if you redshift that galaxy with a redshift of around 10, which is the furthest galaxies that we can see at the moment, then the redshift is pushing all the wavelengths to longer wavelengths. So the ultraviolet gets redshifted all the way through the visible and into the infrared. And then the visible gets shifted further into the infrared, and the infrared gets shifted into even further into the infrared. But what that means is that if you now observe this galaxy, and we know that galaxies have this break called the Lyman break in the ultraviolet, where the flux from the galaxy suddenly cuts off because it all gets absorbed by hydrogen. And so this is a very good distinguishing feature for a galaxy. But if you go to high enough redshift, then that break is in the infrared, and you basically can't see that galaxy at all in the ultraviolet and the visible. And so the line plot here showing the brightness against wavelength is what the spectrum looks like of a galaxy at a redshift of 11, which is the furthest we can possibly see a galaxy right now. And you can see that the galaxy is quite bright in the infrared, but then it drops down in the infrared, and there's nothing there in the ultraviolet and the visible. And that's shown by the images you might take of a galaxy like that, which is basically the image we have from Hubble at the moment, where we don't see the galaxy at all in the ultraviolet or in the visible because there's no light getting through short of this Lyman break. And all we get is we get one filter in the infrared where we get an image, and we kind of have to guess that that's a high redshift galaxy based on just seeing it in one image. But with Hubble, with James Webb rather, we're going to go further out into the infrared. And so we'll get images in 8 different filters, all in the infrared, and we'll be able to characterize the galaxies much better. And we'll be able to get spectra in the infrared as well and really understand these galaxies. So with Hubble, we've really gone as far as we can. We've found the most distant galaxy we can find with Hubble, and we simply can't go further because Hubble doesn't go far enough into the infrared. So there are 4 instruments on James Webb. So there's NIRCam, NIRSPEC, So NIRCam is the main imaging camera. NIRSpec is the main spectrograph. MIRI is the mid-infrared instrument. And then the Canadian instrument is called NIRIS, which stands for the Near Infrared Imager and Slitless Spectrograph. So it is both an imager and a spectrograph. And mostly, though, it's going to be doing spectroscopy. And it has a couple of interesting modes, which are different from the kind of spectroscopy that can be done with NIRSpec. And so this is the field of view of the telescope. So basically all the instruments kind of lie within the field of view, and it is possible to get data from more than one instrument at a time, although we're limited in the amount of data we can download for being able to use. So we can only use 2 instruments at a time. But as well as that, also shown in this plot are the FGS, which is the fine guidance sensor. And that is also provided by Canada. So Canada provided FGS and NIRIS. And the fine guidance sensor is not a science instrument, but it has a really crucial role in all observations, in that it controls the pointing of the telescope and makes sure that we stay locked onto targets. So it's going to be in constant use. And there are basically 2 detectors in the FGS you can see here with these 2 images. And so we pick a star that we know where they are, and we then make sure that the FGS can lock onto that position. And if there's any small movement of that star, there's some drift with the telescope pointing, then there is a mirror that can move very quickly, a small mirror in the telescope to correct that drift. And so this is what FGS and NIRIS looks like. It's about the size of a washing machine. And this is the components that Canada provided to the JWST mission, and this is why our Canadian scientists have access to it. So the team who built and worked on FGS NIRIS, that's Canadian Space Agency, Honeywell Aerospace, who used to be called ComDev, the National Research Council here in Victoria, and also quite a few universities in Canada. And astronomers at all of those universities are now eligible to apply to use the telescope. And we had good success in the first round of open proposals, as you'll hear about later today from Matt, and also in December from Madeline and Wes. So it's been quite a long ride for us for the FGS NIRIS instrument. We started out in Ottawa and then went to Maryland for testing at NASA facility. Then after that, so when we were there, we kind of joined up with the rest of the instruments and the rest of the telescope. And then we went down to Houston and did some tests there. Then went over to Los Angeles, where the spacecraft and the sun shield was all being built, and the telescope got combined with the spacecraft there. And then just recently, we've headed over to French Guiana, and that's where we're going to launch from. So what do we want to do? What kind of science do we want to do with James Webb? There's 4 key science areas. We want to see the first galaxies, measure the evolution of galaxies across all of cosmic time, discover stars and planets, and also study the origin of life. So it really covers a lot of astronomy research these days. It's a very versatile telescope that can do lots of different things and is applicable to many different science areas. And that's why I think it's going to be so exciting during that first year. We're going to get a lot of good discoveries coming out. I was going to tell you a little bit about some of my own research that I'm planning to do with the telescope, specifically in the area of the first galaxies. I've already mentioned about the fact that we hit this limit with Hubble, where we just can't see galaxies further away because of the limit that Hubble doesn't go far enough into the infrared. Whereas with James Webb, we can go, it's a much more infrared optimized telescope. It's a much bigger telescope, so it has better sensitivity, it has better spatial resolution. The 4 instruments that are provided are really high quality instruments and a big improvement over what's on Hubble. So all of these things together are going to help us get much further back in time, and not just detect galaxies earlier than Hubble's able to see them, but we can really characterize galaxies much better than we could with Hubble, which was much more limited in terms of our understanding of what the galaxies were actually like. So the program I'm going to tell you about today is called Canucks, and that's the program led here out of Victoria. And it relies on gravitational lensing, which some of you might be familiar with. The gravitational lensing, we have a galaxy in the background, and that galaxy we want to study, but it's very far away and very small, so it's kind of difficult for us to see with our telescope on Earth or even at L2 with James Webb. So typically the lights, so the white spikes you see in this plot are light rays coming off the galaxy, and they head in all different directions. And those of us that intercept our telescope are the ones that we get to measure things from. But if we now put a heavy mass, such as a galaxy cluster, in between us and that galaxy, then what happens is the mass of that galaxy cluster bends the light. And some of those rays that we're going to miss our observer actually bent towards the observer. And so we basically get more light getting focused like a lens onto our telescope. And so in this case, you may get two actual images of the galaxy and both of them get brightened. But you might also get the spectacular arcs, depending on the exact location of the galaxy compared to the lensing cluster. You can also get features like this lensing arc here, where the galaxy gets deformed and stretched out. And with these kind of observations, we can see details on galaxies that we would never have been able to see without this effect. So in Canucks, we're going to observe 5 of these galaxy cluster fields and study the galaxies behind them. So these are the three Victoria people working on Canucks. On the left side there is Nick Martis, postdoc, working with me, and on the right-hand side is John Hutchings. So the survey, we're going to take images and we're going to take spectra of these clusters and some fields near the clusters as well, using the parallel observing ability of the telescope. So the image on the left there shows you one of these galaxy clusters. This is a simulation of what we'll see with James Webb, where you can see the yellow galaxies are very bright, and those are the galaxies inside the galaxy cluster. And then most of the other galaxies you can see are actually far, far behind the cluster. And those will get gravitationally lensed, some into arcs and some into multiple images. And we'll be able to get much more information on those galaxies because of the increase in their brightnesses and the stretch of their sizes from gravitational lensing. And then on the right-hand side here is a spectrum, simulated spectrum of the same field, where basically each of these objects, you can see each galaxy has been stretched out into a spectrum on the detector instead. And so you can see the spectrum goes from blue to red. This is all in the infrared, but the color scheme there tells you that the blue is the shorter wavelength infrared and the red is the longer wavelength infrared. And so for every galaxy in this field, and there's thousands of galaxies in this field that we can detect with a telescope like James Webb, we'll get a spectrum. And so we'll get thousands of spectra per field, and we have to disentangle them all, but we have software that has been developed to be able to do that, because obviously there'll be some overlap between those spectra. But it's a really powerful way of getting a lot of spectra at once. And those spectra are really key because that's where we get more of the astrophysics and the information than we do just from plain imaging. So here's an example of what you might do with a spectrum. A lot of these galaxies are very far away. They have very strong emission lines where they emit certain elements at specific wavelengths that we know about. And that helps us to determine their redshift, how much the spectrum is being shifted by, but it also allows us to understand the properties of the gas in the galaxies. And so in the panels here, you can see the spectra in the top panels, the ones labeled F115W, etc. And then below that, we subtract the continuum, and all we're left with is the emission line. And this allows us to study the gas, which is emitting this emission, also the dust, which obscures emission line and continuum. And these emission lines are also strongly correlated with the star formation. So it's telling us about the rate of star formation in these galaxies. So the questions we want to understand, like how did the first stars and galaxies form? Where did the elements come from? And what type of galaxies reionize the universe? And this was like a phase transition in the nature of the hydrogen in the universe that happened about 1 billion years after the Big Bang. So to sum up, the James Webb Telescope is ready for launch. It's there. It's only 4 weeks away now. It's hard to believe after 15 years working on this project and a lot of delays. When I started, the launch date was supposed to be 2013. So I have to wait a long time for this moment, but very excited. And I'm going to be heading out to Baltimore to the Mission Operations Center to see the launch. And it's going to be a very exciting time. So James Webb has large mirrors, newer instruments, and the infrared optimization really means that there's going to be a whole load of discoveries that come out once we get past that first 6 months of telescope and instrument commissioning phase. And Canada is really lucky to be a part of this. It's really good that people like John Hutchings worked hard to make sure that Canada could be a part of it, and a major part of it, because we really provided the guidance system and a science instrument. And it's going to be very exciting to see what kind of discoveries people will make. Thank you.
Thank you so much, Dr. Willott. Fascinating look at the telescope, and I'm excited to see what science comes out of it. I have a couple questions from your talk, but first we've got one from Judith and Randall. Are situations that produce gravitational lensing rare or common?
They're rare. So, but we're lucky in that we've got to the point where over the last so many years, we've had a lot of sky surveys that have covered the entire sky with telescopes, X-ray telescopes, optical telescopes. And so we've actually discovered most of these very massive galaxy clusters already through those surveys. So we know exactly where they are, and we know where to point. So they are quite rare, especially the ones that are really good. So we combed through a short list of about 30 different galaxy clusters to choose these 5 that we're going to observe with, to really the best ones that we can. And these have all been studied well with Hubble as well, which is quite important for us because Hubble provides the optical information and James Webb provides the infrared.
So you'll be able to match up those 2 data sets.
Yep, exactly.
Okay. One of my questions was on that Lyman drop that lets you distinguish galaxies. So is that one of the main features that is why you went with like an infrared telescope rather than something like a microwave telescope for looking for first galaxies, or does stuff not get shifted down enough towards microwave to be able to look for it?
That's a good question. Stuff only shifts by a factor of about 10, and the infrared is actually quite large. Between the near infrared and the far infrared is a factor of 100 or so. So the shift is a small amount, but the question is, what's the physical properties of the emission that you expect to see? So what we usually see, let's just go back to that one. What we usually see, or certainly what we're expecting when we design this telescope, is that we're looking for the ultraviolet emission that has then been shifted into the near infrared. Because if we look at what we think are young galaxies in the nearby universe, they have a lot of ultraviolet emission. They have a lot of hot stars. And as you know, hot stars are bluer. They provide a lot more of their emission in the ultraviolet than elsewhere. But also, as we look further back in time, we don't see as much dust. And so if you're observing in the microwave millimeter, say with ALMA, then you're looking at the dust and the molecules in the atoms in the interstellar medium. We don't see so much of that, although ALMA has been able to detect some very distant galaxies. But we're thinking that the key observation is going to be these very hot young stars in the ultraviolet. And so the galaxy is going to be brightest in these wavelengths.
Okay, so
and this is exactly where we designed NIRISS to operate. So NIRISS is operating in this part of the near infrared for the spectroscopy. And so we'll be able to get spectra like the one shown here, where we see clearly this break, but then also get more properties of the galaxy as well.
Yeah, so basically you could see some features in microwave, but they tend to be dimmer and don't really correspond well to a lot of the stuff we've studied well in galaxies. In optical.
Yeah, that's right. And I mean, and we do have ALMA on the ground, which is, obviously your wavelengths. You need a much bigger telescope if you're observing at longer wavelengths than the millimeter. So we do have ALMA on the ground, which actually is really good. And in fact, most of these fields have also been observed with ALMA. So we're going to be able to compare like the galaxies we find and see if they've been detected with ALMA as well. But with ALMA, generally, a lot of these early galaxies, they're not seen with ALMA because they seem to be quite poor in dust. So not much dust is formed in them. They've formed lots of hot young stars, but not much dust.
Okay. Oh, and we've got a couple more questions coming up. Let's see. Dennis asks, how long will James Webb operate?
Well, the baseline mission is 5 years of science operations after the first 6 months. We're hoping it goes to 10 or 11 and possibly even longer. Okay. So there is fuel on board for pointing the telescope, and that is the thing that's expected to run out at some point. But if all goes well with the launch and getting us to L2, we should have a lot of fuel for a long mission. And then it's just a question of whether things break. So we can't really do much about that because it's too far away for us to go and fix it if something breaks.
Mm-hmm. Doesn't it have like a hard upper limit in terms of the coolant?
No, because it doesn't use coolant that evaporates off. So the 3 near-infrared instruments are passively cooled, so there is no coolant for them. They're just protected by the sun shield. And then the mid-infrared instrument is cooled, but it's a closed cycle cooler that doesn't leak, so that should last a long time.
Let's see. And Bernard asks, what were the main reasons for the delay in the launch of the telescope?
Yeah, okay, there were numerous, but the longest one, particularly over the last few years, has been the sun shield. So the sun shield, it's a one-off, first of its kind, and maybe the last of its kind, I don't know. It was very difficult, but maybe now it's been produced, they know how to do it, they can do another one easier, but it turned out to be very difficult to make the sun shield that was very reliable. You saw how folded up it is, and then it has to unfold itself, and it has the 5 layers. There's a lot of things that had to be done with the sun shield to get it reliable. So there were a lot of tests, we go through these cycles of where we'd, fold it up and then unfurl it and then pack it up. And each one of those took months and months. And we had to go through more of those than we expected because each time we did it, something went wrong. But the last time, everything went perfectly. And we think we understand all the things that can go wrong. But certainly, when that sun shield is fully out and deployed, I'll be very happy and a lot less nervous.
Yeah. Let's see. We've got quite a few questions here. Might have to save some of them for after. Let's see. Oh, here's a quick one. Is there any reason why the outer part of the sun shield is pink? That's from Mary.
The pink is mostly just the covers. So the pinker covers that get basically rolled off at the end. So when it's actually out, it's mostly not going to be pink. It'll be more the kind of silver color.
Okay.
That's on the picture.
All right. Let's see. Just wanting to double check that we have Dr. Taylor in. Yes, he's on there. So
right here.
Excellent. So I think we'll move along to Dr. Taylor's talk, and then if we have time afterwards, I may bring back some more questions for Dr. Willott as well. But I am keeping an eye on all of the questions in the chat, so we'll get to as many of them as we can. So with that, welcome, Dr. Taylor.
Yeah, hi. Thanks for having me. I'm actually speaking from a bed and breakfast in Calgary at the moment. My wife is behind me, so I'm just going to have to speak from the black void of Zoom if you don't mind. But nonetheless, I think I can hopefully give you a somewhat interesting talk. So I'll just share my screen here. Are you seeing that?
Yes, we are.
Awesome. Yeah, so I'll just dive right in then, I guess. Sounds
good.
Yeah, my name is Matt Taylor. I'm from the Comox Valley originally. I did my undergraduate studies at UVic, my PhD down in Chile. Spent a bit of time in Hawaii at Gemini Observatory before coming back to Victoria for the last couple of years to work with Pat Cote and Laura Ferrarese here at Hertzberg. And I'm actually going to be moving to University of Calgary come January. That's why I'm here, is just doing a house hunting trip. Regardless, I am really, really happy to tell you about my accepted Webb program for Cycle 1. I was lucky enough to be awarded slightly over 40 hours to carry out this program, which the sort of overarching goal is to search for what are called intermediate mass black holes in the middle of compact stellar systems in the Virgo galaxy cluster. And so these, the systems that I'm actually going to be talking about and actually studying for this study are very much not the galaxies that I'm showing on this slide. So I'm showing these galaxies mostly just to satisfy our love of beautiful images of grand design spirals and whatnot. It's always nice to show a few of these. But more importantly, what's unique to these galaxies is that basically every single one is basically guaranteed to harbor a supermassive black hole in the core of these, the nuclei of these galaxies. And so supermassive black holes are black holes that have achieved a mass of over sort of a few million times the mass of our sun. And so these are thought to be to sort of form very, very early in the universe and rapidly accrete matter to grow to the sizes that we observe in the local universe. But there's still kind of some tension as to exactly the mechanism of how they achieve these masses. And very broadly, you can kind of separate these ideas into two camps. One where these black holes start from very small seeds. So we're thinking, tens or maybe a few hundreds of solar masses, and then grow from those relatively small sizes. Or they might actually start from very high mass black holes and grow from there. So what's interesting is that both of these theories, they can produce the same number of supermassive black holes that we actually observe, but they actually predict very differing what are called occupation fractions of what are called intermediate mass black holes. So these are kind of in between supermassive and stellar mass. And so these theories predict different frequencies of these intermediate mass black holes existing in low mass stellar systems. So for example, if these supermassive black holes grow from very high mass seeds, then we would not expect to see very many intermediate mass black holes in low mass stellar systems today. On the other hand, if the light seed scenario is correct, then we'd expect to see a lot more of these intermediate mass black holes in low mass stellar systems. And so that's really the overarching question that this program is trying to get at. And so switching to sort of a more schematic look, this is the famous Hubble tuning fork diagram that's been around for a long, long time. And it's sort of a nice way to visually classify galaxies into sort of spiral or elliptical. And it's somewhat of an evolutionary sequence in that the galaxies more to the right will typically be lower in mass than the galaxies towards the left. But if you go farther to the right and into the sort of the dwarf galaxy regime, this nice sort of tuning fork diagram breaks down, and it's not really clear where to put sort of dwarf galaxies and what are called compact stellar systems on this diagram. One of the reasons is that there's quite a few evolutionary connections between these low mass stellar systems. So for example, here on the right, I'm showing sort of more compact systems like globular clusters, what are called ultra compact dwarf galaxies or compact elliptical galaxies. And in the environment of like a really rich galaxy cluster, the environment can be so violent that these low mass systems can actually be rapidly transformed into these sort of light, fluffy dwarf galaxies and have all that sort of fluffiness stripped away and only leaving sort of the compact cores if they exist in the first place in these galaxies. And so these evolutionary connections make it quite tricky to kind of nicely place these low mass systems on such a nice kind of diagram like the Hubble tuning fork. So let's talk a little bit more into what I mean by low mass stellar systems, make it a little bit more clear what I'm really targeting here. So these broadly fall into a few camps. Globular clusters and nuclear star clusters are kind of the arguably the lowest mass. So these are star clusters that are up to a few 100,000 stars, but contained into only a few parsecs in size. So these are some of the most compact stellar systems that we know in the universe. And so these are compact enough that they can survive multiple passages through an environment like a galaxy cluster. The only real difference between globular clusters and nuclear star clusters is that globular clusters can be found all around galaxies, whereas nuclear star clusters are found exclusively in the cores, so right in the centers of galaxies. Next are the more high mass counterparts called ultra compact dwarf galaxies. So these are systems that have the mass of entire dwarf galaxies, but contained into much, 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 much smaller volumes. And so these are broadly thought to be the remnants of dwarf galaxies that had a lot of their sort of fluffy material stripped from them. Next is just your standard kind of classical dwarf galaxies. So these can come in sort of nucleated flavors with nuclear star clusters or non-nucleated. These are found around giant galaxies all through the universe. They're the most numerically common type of galaxy in the universe. So they're very, very common and useful cosmologically. And so these are kind of the three that we're targeting in this program. We're not targeting globular clusters in this program specifically because we know that they're not galactic in origin. Star clusters form alongside galaxies, but they're not remnants of galaxies. They didn't used to be galaxies themselves. And so seeing as we're trying to identify black holes that are presumably coming from galaxies, we're not very interested in targeting globular clusters, at least not for this program. So dwarf galaxies, I won't belabor this point too much because I've already talked about them, but like I've said, they're the most numerically dominant type of galaxies in the universe. They're cosmologically interesting because we don't seem to observe as many as a lot of the cosmological models seem to predict. They come in a few different flavors between very high star formation called dwarf irregular galaxies, the more classical kind of red and dead galaxies. These are dwarfs that are not actively forming stars. These are your classical dwarf spheroidals, dwarf ellipticals, and nucleated dwarf ellipticals. And then there's even sort of tidal dwarf galaxies, which actually form through tidal interactions that are not thought to have dark matter in them because they're actually formed sort of more through baryonic arguments. But when you do have nucleated dwarfs, these are kind of examples of what can lead to nuclear star clusters and ultra-compact dwarfs. And so as an example of both, these images are showing U, G, and I band images of a few different dwarf galaxies. And what we can do is we can actually sort of fit a 2D mathematical description of the light profile to its very diffuse light to get a really good description of that component of the galaxy and subtract it off. And when we do that, then you'll actually see in the sort of the bottom panels of these two sextants is when we subtract that diffuse light off, we're just left with these really, really tight cores. And so these are the nuclear star clusters and ultra-compact dwarfs sort of before they've been stripped in these cluster environments. And so if we think that these are galactic in origin, then we might expect them, like giant galaxies, to have these black holes in the middle. It took a long time to actually get proof of this. Some people thought that ultra-compact dwarfs were actually just giant globular clusters, and so weren't galactic in origin at all. But in 2014, there was a really exciting paper that came out by Anil Seth's group. And this is a diagram that's being shown on the right here, where they took an integral field unit, which is basically an imager, but instead of just getting photons collected at all wavelengths per pixel, you actually get a spectrum at each pixel location. So they're kind of 3D data cubes. You can kind of picture rotating these 2D images in 3D space, and then have sort of spectra extending behind them. And so, as Chris nicely pointed out, spectra are very handy for determining redshifts and velocities. And so that's what's shown in this map here. So the left column there is showing just the straight radial velocities. So these are the stellar velocities along our observational line of sight. And in the right-hand column, it's actually showing what's called the velocity dispersion. So this is the spread of stellar velocities in a given pixel. Given that each pixel contains an unknown number of stars, all of those stars are going to have slightly different velocities. And so the spread of those velocities is what's shown in that right-hand column. The top rows are showing the actual observed data, and the bottom row is actually showing their model that incorporates any black hole that might be there. And so lo and behold, if you look in the right-hand column, you'll see a sudden spike of red right in the middle of both the model data and the observed data. And this is indicative of the presence of a supermassive black hole where the gravity is so strong that any stars that are around it suddenly get whipped to really, really, really high velocities. But any stars outside of the gravitational influence are at much more sort of normal speeds. So whenever you see a sudden cusp in the velocity dispersion like this, it's absolute smoking gun evidence that there must be a very massive black hole in the middle. So this was a really, really exciting result, and it was rapidly followed up by about maybe half a dozen other detections in other systems. But unfortunately, technologically, we hit a dead end where we just cannot do this anymore without more technology. Enter James Webb. Actually, I'm just going to skip over this because I've kind of already explained this. So enter James Webb, where we can actually start to study a lot more systems and start to probe parameter space in a much richer fashion than we've ever been able to do before. So as an example, this diagram is actually showing along the x-axis the size, with size increasing to the left, not the right, against mass along the y-axis. So you see really giant galaxies. So giant ellipticals and spirals are up in the upper left, whereas the more compact globular clusters and UCDs are kind of more in the lower right. And so you'll notice that there's this big gap between these kind of more galaxy populations to the left and the compact populations to the right. One of the questions is whether this gap is real or whether it's actually transitory. And so, but what I mean by that is, do we not find any objects in this gap very often because there's truly never any there? Or are galaxies transforming between these populations, but they happen so fast that we just never see them in the act of this transformation? And so this is the program that we're trying to get at. And so these arrows are kind of illustrating what I'm talking about here, where giant ellipticals can transform into compact ellipticals, kind of basically along these arrow directions, and nucleated dwarfs can turn into to UCDs, and yeah, so just kind of illustrating some of these evolutionary connections. So James Webb is finally going to kick down the door and allow us to do these kind of studies. And so this is what we were given the 40 hours to do. So we're going to be studying 18 compact stellar systems, ranging from compact ellipticals at very high masses all the way down to nuclear star clusters, 10,000 times less massive than compact ellipticals. So we're really probing a huge range of compact stellar systems that might be coming from a huge range of galactic hosts. And so we're going to be trying to probe to find out whether intermediate mass black holes even exist, how commonly they exist in low mass stellar systems like what I've been talking about. And the frequency that they do exist is going to be really powerful in informing exactly how supermassive black holes formed early in cosmic time. And so this is just an example. This is the Virgo galaxy cluster. The color is just indicating kind of density of galaxies. So where it's yellow, you find a lot of galaxies. Where it's blue, you don't find many. The colored stars are all of our targets, and so you'll see they're probing sort of three main components of the Virgo galaxy clusters. These are three sort of galaxy subclusters that are all coalescing together. And then we're also going to be probing a few targets in the intercluster medium. So this is really going to have a nice sampling of this particular galaxy cluster with a really nice range of targets to hopefully provide some really interesting scientific results. And so this is, I'll skip over this because I think I'm going a little bit long, but this is just kind of explaining how we're doing it. So this diagram in the upper right here is showing an example of band heads that are coming from carbon monoxide. So these are actually going to be the spectral features that we'll be measuring to get the radial velocities and the velocity dispersions to create the maps very similar to what Anil Seth did back in 2014. Only our maps are going to be much higher fidelity, given that it's coming from James Webb and the NIRSPIC integral field unit. And so, yeah, really looking forward to James Webb. We're going to be deriving new scaling relations for black holes and their galactic hosts. We're going to be confirming whether intermediate mass black holes exist, which seems like a simple question, but it's currently very hotly debated in the literature. So this should be a really great result to say whether they do or not. And if they do, then this should really greatly inform these two competing scenarios for supermassive black hole formation. And so hopefully if this is successful and we get some results, then this will represent a really nice sort of pilot study that we can then take forward into more galaxy clusters as James Webb gets used in the future. So yeah, I'll leave it at that, and I'm happy to take any questions.
Thanks very much, Dr. Taylor. Yeah, so I've got a few questions. So I have one that may tie into a bit of Chris's talk as well, in maybe he can talk about how it's going to be done on the James Webb. So how did Seth get so much spectral data out of single pixels on that during that initial study?
Well, two things really. Number one, they integrated for a long time. So the reason, I mean, we strictly speaking, we can do more of this science from the ground. But to give you an idea, we did put in a proposal to do a UCD that was not that much fainter than the one Seth studied. But to do that, we required over 20 hours per object on an 8-meter class telescope, just to give you an idea of just how unfeasible it is from the ground. And so the reason that Anil was able to get this data was because they picked one of the brightest ultra compact dwarfs known. And so that really minimized the amount of telescope time they required, and then maximized their signal to noise per pixel so that they could get this really, really nice kinematic map.
And just to clarify the question, I think the question is like, what sort of instrument was being used as well?
Oh, I see. Sorry. Yeah. So this was, I believe it was NIFS, the near infrared integral field unit on Gemini North.
Okay. And that one, just for folks' information, so an integral field spectrograph basically takes a spectrum at each slice of the image. So it takes the image, slices it up into bands 1 or 2 pixels wide, and then takes spectrum from each of those bands. So you get essentially a map of the entire field where you have a spectrum from every single point on the image.
Yeah, essentially, that's the image slicer style. There's also a lenslet array style, but we don't have to go into that. But yeah, so yeah, the image slicer is the NIFS design, where it's like taking essentially like taking a whole bunch of long slit spectra and just sort of sticking them side by side, so you get a nice 2D array of spectra.
Yeah, and that takes a lot more integration time than you'd need for just a single spectrum, right?
No, well, that's the power of the integral field unit is rather than limiting to a single slice, or sorry, rather than limiting it to only the light that comes through a single slit, the image slicer essentially can stick it into, a dozen slits or more, depending on the IFU design. So you can actually get essentially like 10 slits all at once, but all together.
Fantastic. Okay. And to tie this back to James Webb, on the Canadian instrument NIR-ISS, NIRISS?
That's right, NIRISS.
All right, I remembered. Yeah, you showed an image before of a galaxy cluster that had a whole bunch of spectra on it. Is NIRISS using a similar technique? Is it an integral field spectrograph, or it looked like it might be just throwing the image onto a grating and getting a spectrum that way?
Yeah, that's right. So so NIRSpec has the integral field unit that Matt's going to use, but NIRISS has a grism basically that just disperses the light, and so it just disperses the light from every single source in the field onto the detector, and spreads out the spectra of everything there. So you get them all at the same time. So you get more information, but you also get more of the background and the overlapping spectra. So it gets a bit more complicated.
Okay, very cool. Thank you.
Also, the NIRSpec, the IFU is a very, very small field of view. So you can see, for example, in these postage stamps, the blue kind of hatching is actually the footprint of the IFU, and so you can see it's very, very well matched to these objects. But you have to remember these objects are very, very compact. And even then, the field of view just barely covers them. So that's something to bear in mind with IFUs as well.
Okay. Let's see. I think those are the only questions specifically for Matt's talk. But we've got a couple.
Oh, Aaron, I had a question. Sorry, I didn't put it in the chat. I'm wondering if Dr. Taylor could go back to the slide almost at the beginning where the spectrum were all kind of all over the place and showing the spectra compared to the globular cluster. It was close to the front. One, I think, couple more. Sorry, I thought there was one. I thought there was one where you had maybe it was in Chris's. Was it in yours, Chris? That you had the different stars and then all the overlapping spectra.
Yeah, that's right.
That was in yours. Is that okay if I go back to that? Sorry.
Sure, I can pull that up. The one, it's the one I was just talking about. So that's nearest using the GRISM where we have, so it's a 2-arc minute field of view, whereas the near spec IFU that Matt's talking about is a 3-arc second field of view. This is now a 2-arc minute field of view, so it's much larger and gets all these galaxies at once.
So I don't know an awful lot about this at all, so I'm going to go way back. In that, is the size? Are you looking at the length of the spectra? Are you looking at the width of it? Are you looking at at how bright they are compared to the ones in the background? Like, what kind of things are you looking for there?
Yeah, I mean, basically each one, although on this plot, you really just see, each of these spectra seem to look the same on this plot, but you're looking at the intensity as a function of wavelength. So we'll see the same as Matt showed the spectral features of the CO absorption. Here we're able to see some absorption and emission features in the spectra. And so I guess this one's a bit clearer here. So here we're basically just concentrating on the spectra of one of those objects, and with the blue and the green and the red spectra shown separately here, from left to right. And you can see the very bright kind of lumps of the emission lines, as well as the continuum. So we have the shape of the continuum, and any breaks in the continuum can tell us about the stars in the galaxy. And then these emission lines tell us about the gas in the galaxy.
Okay.
Yeah, so it's like a bunch of really low resolution spectra. You can pull out a couple of features from those. And if you go back one more, back to that one, there are a couple of just red spots in the image. Are those first galaxies where you only are seeing the little bit that pokes into the infrared?
No, they're not that exciting, unfortunately.
Oh, no.
Yeah, those are one of the features of the GRISM spectroscopy, in that as well as getting the spectrum you want, there's also what's called a zeroth order, where some light kind of passes through and doesn't get dispersed. So those are basically. Those are also, each one of those will line up to a galaxy, on the left-hand plot, and each one lines up to one of these spectra, but it's offset in wavelength. But again, we know where those are, and we can deal with the fact that they're there as well. So
yeah, and then you can correlate each of those to the spectra that are coming off.
That's right. Yeah.
I see.
Aaron's explanation sounded way more interesting.
I thought I was being so clever. Let's see. Another question from Matt. So one of the science goals for the James Webb is looking at the evolution of galaxies. So is the James Webb Space Telescope going to look at the relationship between dark matter and supermassive black holes as well?
Yeah, I mean, that's a good question. Yeah, I mean, you would think because supermassive black holes kind of dominate the dynamics in the cores of galaxies, you would think that there would be this tight relationship between the two. But in fact, it's really the dark matter halo that does most of the interacting in kind of a galaxy cluster environment. So, for example, if a galaxy falls into a galaxy cluster, you'll strip the dark matter halo before you strip globular clusters out of the halo, and you'll strip the globular clusters before you start stripping the diffuse stars. So by the time that you really kind of get to the level of like a black hole that might be left over, it really doesn't have much to do with dark matter, because most of it has already been stripped from the galaxy. So in these kind of systems, given that there's some more galactic remnants, they really don't have too much to say other than the size of the black hole that, size of the dark matter halo that it used to be embedded in. You could put some constraints on that, but not really much in terms of sort of evolutionary arguments.
Okay. Yeah, but we do see a relationship between a black hole mass and a dark matter halo for larger galaxies that haven't been disrupted in this way, right?
Yeah. Yeah.
Okay. Okay. Let's see. I think I've got one or two more. Got to scroll back up into the chat. Yeah, so another one from Dawn. This one's for Dr. Willott. What was the hardest engineering challenge with this telescope?
Well, the sun shield really has been the hardest part for the whole telescope. That's been the thing that's been the most complicated and most tested. Here within Canada, we had our own issues as well, although quite a while ago. Originally, the NIRISS instrument didn't have the GRISMs in it, and was planning to do kind of quite different science. The original plan had a tunable filter where we would be able to change the wavelength of which the filter works, and basically take images in at any wavelength that we wanted. And so we'd take a whole bunch of images at different wavelengths and just do images instead of spectroscopy. But it turned out that it was very difficult to build that to operate in space. And after quite a bit of trying, eventually the team had to give up and pivot very quickly. And we very quickly managed to have this other plan with NIRISS, where we can take GRISM spectroscopy, not only of the galaxies that I showed, but there's also a very powerful exoplanet atmosphere spectroscopy mode as well with NIRISS, which I didn't have time to talk about today, but there'll be quite a lot of observations with that done in the first cycle as well. So I think in the end, we're pretty happy with the instrument we ended up with, and it's probably better that in terms of the science we can do, the instrument we have now than the instrument we would have had if we'd had the narrowband imager working.
Thank you. And I think last question before we move on to our Ask an Astronomer section. What worries both of you the most about deployment? I imagine the sun shield's going to feature heavily, but maybe what's your second most as well?
Well, I mean, the solar panels obviously are important, but solar panels, they're pretty reliable. They happen, they have them on a lot of things. But the solar panels are really critical here because we have a battery, but the battery only lasts 12 hours. So if we don't get the solar panels deployed within that first 12 hours, then we basically run out of energy to do anything. So that would be disastrous. But so I'm not too worried about those, although obviously, as soon as we get those out, that's going to be really, a good thing. But, I'm looking forward to seeing the real sky as well, what the sky looks like once the telescope's cooled down and once we get the first images, and checking that NIRISS is still the same, as it was when we last operated it. We haven't put light through NIRISS since 2017. It's been, sitting there. We've, turned on the electrical systems and tested some things since many times, including just a couple of weeks ago in Kourou. But we haven't actually, shone light through the instrument in 4 years. And so, checking that everything's still working there is going to be important.
Yeah.
Aaron, I asked this like a long time ago, so it could have gotten lost. Is for the sun shield itself, it's made of all these layers. What are the layers actually made of? What is the material that the layers are made of?
Right, it's a special type of plastic. So it has to be very strong, but it also has to be very light and very thin. But it has to be light because it's obviously a very large area we need to cover, and yet we want it to not weigh very much because we need to pack it all into the rocket and be able to deploy it.
And how many materials were tried before you got to the one that you ended up with?
That's a good question. I wasn't there, I guess, when they were doing the development of the sun shield, like the original materials back, because that's like 10 years ago, or more. So I wasn't really involved in the detailed hardware at that point. So I'm not sure, but I know several changes were made to the sun shield design, along the way.
Yeah.
Okay, thank you.
And sorry, just to give Matt a chance to answer the previous question on what he's most worried about for James Webb launch.
I mean, when it comes to the technical stuff, I trust the folks at CSA and NASA. They seem to do pretty good work. So I'm not really at a point where I can find something technically to worry about. But what I worry about is the fact that they gave me time on the telescope without taking into account my luck. So really that's what I'm worried about, is my personal luck is going to somehow screw something up. But there's not much I can do about that, I'm afraid.
Well, we'll be sure to direct all the angry emails your way then.
Yeah, Matt, are you going to be watching the launch?
Oh, you bet.
It's going to be pretty early in the morning here in the West.
I'm going to be up. I'm going to be up for it for sure.
I don't think that matters, Chris. For those that are interested, I don't think that matters.
Yeah.
And sorry, I just realized I missed one last question here from Janine. How will the initial ionization of the universe be determined?
That's a good question. One of the other projects I'm working on actually uses NearSpec and is taking spectra of quasars in the early universe. And those quasars, because they're very powerful light sources, they have a lot of UV emission. We can measure the absorption in the UV emission. And from that, we can determine how the ionization, which elements are being ionized, and determine the ionization state of the universe as a function of different times. So looking forward to that as well.
That's very neat. And so that UV light will be shifted into the ultraviolet band about the same amount as you'd see for those first galaxies.
That's right. The UV is shifted into the infrared as well. Yeah.
Gotcha. All right. Well, thank you both so much, Dr. Willott and Dr. Taylor. Loved learning more about the James Webb Space Telescope, and I'm really excited to see the science that it's going to be doing. Fingers crossed once it gets up there and deployment goes successfully.
Thanks.
So Aaron, I have a video on JWST to share, so if I can do that.
Absolutely.
Okay. I'll share my screen. So here we go. So this is a video I recorded of myself using the Webb-inar app that the people at the Space Telescope Institute have developed. It's a VR app. I run it on my Oculus Rift. It's actually very cool. So this is just a little bit of a brief video I put together quickly this afternoon. So here we go. This is Webb-inar. So here I am kind of jerking around. So in my left hand, I have a little control tablet that I can bring up to do things. So here I am moving towards the telescope. So I want to see, well, how big is this telescope really is? So let's bring up something here. Let's bring up, compare it to Hubble. So there we have the size of Hubble compared to the size of JWST. And you can see JWST is quite a bit larger. About something like a car. There's a car. Okay, well, that red sports car, I don't know if it's a Tesla, but it's pretty small compared to the size of both Hubble and JWST. And then let's put an elephant in space because we can. And there we have size of an elephant compared to the telescopes. So anyways, that's kind of fun. You can fly around and do various things. So one of the other things you can do is visit Saturn. And so here I visited Saturn. I'm flying around its rings, maybe into the planet actually. One of the things I discovered as I was jetting along here, there actually is, they have probes around Saturn in this virtual reality experience. So there's one of them. I just came whizzing by me or whatever, and there's another one. And so the various probes around Saturn are there, Cassini. And again, you can fly through the rings. You can do all sorts of things, visit the other planets. One of the cool things that I really like doing when I'm in here is visiting black holes. And here we have a supermassive black hole. And if I pull the trigger, I can shoot a star into the black hole. And when it hits the black hole, all these jets fly out the poles. So you can just fire star after star into the black hole and create these polar jets. And watch, if you do it at the right angle, the star won't go into the black hole right away. It will orbit around the star, the black hole, and eventually get merged into the black hole. And again, there's opportunities to learn about the science behind all this. You can go and look at things like extrasolar planets. So here we have planets around a nearby star, and but you can visit an observation lab. Again, it's really a very extensive VR experience. It's not just fun to do, which it is, but you can actually learn and learn a lot about the science that that James Webb will be doing. And I think the last thing, if I don't, if I get a little too close to this star, there we go. Anyways, it's quite safe to do this. You might fall off your chair. The last thing I'm going to do is go and look at circumstellar disk here, if I remember right. Protoplanetary disk. Yes. Let's go. Oops. No, I'm going back home. Sorry, I did that in an earlier experiment. So here I'm just going to do a little fly around the telescope. There we are. We're back. So as Chris explained, there's the primary, the secondary, the sun shield, and if we come around behind it, we'll see where all the instruments are stored, and all the data will be gathered with instruments in the instrument module here, and it's all nicely insulated. And I presume that big antenna at the bottom there is the antenna that will send the data back to Earth. So anyways, if you have a VR headset, I really say if you haven't seen it, the Webb experience is a very cool thing and a lot of fun. And if you have other headsets, I mean, there's lots of great astronomy apps available. So that's it.
And we just have a
Thank you,
new
Dennis.
Rift VR at the center, and we'll have to put that on. Put that one on. So as soon as people can come up and visit, we'll have that ready for everybody to have a look.
I can't say how much fun it is. So, and the thing is, I didn't do it, but you can fly up and be at the top of that jet looking down. And so you fire a star in, and you're right in the middle of the beam of material that gets ejected. It's really cool.
Mm-hmm.
So.
All right, thanks so much, Dennis. Next up, we have our Ask an Astronomer segment, and Jonathan Rinaldo, a student at UVic in the Physics and Astronomy department, is going to be joining us. And I believe our guest speakers are going to be joining him as well to answer any questions you have about astronomy, space, the universe in general. Welcome, Jonathan. Let's see. I don't believe we have Amy tonight to ask questions, so
that's correct.
Okay. Let's see. Calvin, do we have any questions from over on YouTube? Yeah.
Nope, we do not yet, but they are welcome to ask them, and we'll get to them probably.
Okay.
We're I think ahead on time, so.
Okay. And I'd like to invite anyone on the Zoom call as well to toss in any questions you have, and not just about our speakers' talks, but about anything you might have for astronomy, the universe, everything, what we've had for lunch, anything like that. Let's see. I think I might have actually gone through all the questions that have come up. Or actually, here we go. Dawn asks about, for the James Webb Telescope, if it's possible to service robotically. If there's any thoughts about remote servicing, like has anything, I know the Hubble was not designed for repairability at all, but has any thought been given to any future tinkering with the James Webb?
Yeah, well, the thing about James Webb is that if we want to save our fuel for the full mission, we need to send it straight off to L2 right at the start. So we can't kind of put it into Earth orbit and then check everything works and go and fix it before we send it over there. So we've basically taken the strategy, and the reason it's been delayed so much has been testing. We've just tested and tested on the ground, and we're hoping that it's all going to work because, you know, we know what the manned spaceflight capabilities are at the moment. You know, we're pretty good at getting to the International Space Station and back, but that's about it. So getting it over to L2 and back is a huge mission that will take years to work on, and it's unlikely that such a thing would happen. The telescope hasn't been designed to be able to be serviced, so we're expecting that if things don't work, that's it, and we'll turn our attention to the next telescope that we'll build instead.
That's fair. We have another question from Lori. Let's start with Jonathan and move on from there. Oops. Can you talk a little bit more about the Lagrange points and why it's stable? Why you can like park a telescope there? Oh, can't hear you, Jonathan. Jonathan, we're not getting your audio.
Oh, you're not?
Oh,
you're very
there
quiet.
We go. You're very, very, very quiet.
How's this?
Much
There you
better.
go.
Thank you.
There we go. All right, so what are we talking about? Lagrange points?
Mm-hmm.
Okay, so the basic concept of that, about why they exist and how they work, is that normally when we think about orbits in space, we think about a small object orbiting one larger object, and the gravitational force of the large object acts on the smaller object, and the velocities are just right to keep it going in a stable path. But when you have two large objects and one small object in an orbit, the force of gravity from both of the large objects exerts a force on the orbiting object. So in this case, both the Earth and the Sun are exerting gravitational force on the James Webb telescope. So normally at orbits farther away from the Sun, you move in a slower velocity, but since the Earth is also between you and the Sun, you experience a bit more force pulling on you, so you get sped up a little bit, and you can actually orbit around the Sun at the same speed as the Earth at that particular Lagrange point. There are 5 different types of Lagrange points. If you ever heard of the Trojan asteroids, they are, I believe, at L2 and L3 in Jupiter's orbit. I may be getting that wrong. I don't have all the different numbers.
L4 and L5.
Okay.
The first 2 are on the line.
Yeah, that makes sense. So basically, there's a point in the orbit of Jupiter where the gravity from Jupiter and the gravity from the Sun balance out just in such a way that asteroids tend to collect in that region. And that's where these Trojan asteroids are found. And I believe there's a space mission being sent there sometime in the near future called Lucy, I believe. I'm not sure when that's launching, but that will be sending a probe to those asteroids to learn more about them and how they came to be and other such interesting things.
Yeah, and I've just brought up a diagram of the Lagrange points, if that helps.
Yeah, so L1 is between, in this case, the Earth and the Sun. So I guess in that case, instead of the Earth speeding you up, the Earth is slowing you down. So you still orbit in the same time it takes the Earth to orbit. But since some of the mass is pulling you one way and some of the mass is pulling you the other way, the net result is that if you were to simplify it to a model where there's only one large object that you're orbiting around, it would be of a lower mass than the Sun is. So the orbit would be at the same velocity, or not the same velocity, but the same period as the Earth.
And for why it's stable, oh, no, that's not what I want. If you look at this one here, so this is showing like this strength of the gravitational field at the different Lagrange points. And at L4 and L5, those ones are unstable. And you can see it's like they're at the top of a hill. In any direction you go, you'll eventually fall off the hill. But in L2 and L1, you've got to dip one way and then a hill the other. So you only have to keep yourself from falling off the hill in one of those directions. If you're rolling sort of the other way, you'll just fall back into that valley. And so the James Webb only has to station keep in sort of one direction, and that saves fuel. Let's see.
So has that been, as knowing that the James Webb would go to L2, is that something that was kind of decided back in the 1990s when it first was going up? I mean, is that one of the kind of the first things that was a deciding factor on the Hubble? Sorry, on the James Webb?
Yes, yeah, that was there right from the beginning, the plan to go to L2. And we're not going to be exactly at the L2 point, because if you imagine, if you're at exactly the L2 point, if you look back towards the Earth and the Sun, they're in a perfect line. And so the Sun's actually going to be blocked out from your solar panels by the Earth.
Yeah.
And you don't actually want that. So we're actually going to be in what's called a halo orbit around L2. So we're going to be in an orbit that kind of goes up out of the plane of the solar system and down and go through an orbit around the L2 point. But it is quite stable there. So it doesn't take much fuel to keep us in that halo orbit. And we can use most of our fuel for actually pointing the telescope to all the different targets we want to point at.
Okay. Speaking of, David asks, how long can the telescope remain at L2 based on the fuel it has?
Yeah, it's a long time. I mean, as I said, like most of the fuel is going to be spent actually going and pointing at different targets. So it's really a question of how long that lasts. And eventually, when we run out of fuel, it will kind of fall out of this halo orbit of L2 and drift off somewhere else. Okay. But yeah, we're hoping to get more than 10 years out of it. So certainly, it's been 20 years in the making, and so for a replacement for the next, great telescope that's going to be better than James Webb, we're looking at least 20 years from now till that can get launched. So we really need this one to last a long time, so we don't have a gap in our capabilities. We've been lucky really that Hubble has lasted so long, going for 30 years. Because that wasn't expected to last so long. And it's great that it's managed to continue all the way up until James Webb is launched and beyond.
Mm-hmm.
I just posted in the chat for people on Zoom a little webpage talking about the early years of JWST. And so apparently, I didn't realize this, but the development of JWST started in 1985 as a concept. So yeah, so that's 15 plus 20, that's 35 years ago, 36 years ago.
Mm-hmm. So, yeah, these flagship projects typically start very, very, a lot earlier than people think. We're seeing that with the 30-meter telescope. Like, I think talks on that started something like 15 years ago.
Oh, more than that.
Yeah.
I call it the TYT, the 30-year telescope.
I have a question, I guess a bit of a thought experiment. Does the L2, like the theoretical L2 point, does it lag behind the Earth due to the light delay in terms of how fast the gravitational field propagates? Like, is it exactly on the line between the Earth and the Sun, or is it like a little behind?
I mean, it's a tiny effect, so I'm not sure. I don't know if it's actually gonna, if it's in a line or if there's a change. I mean, it's pretty general relativity by that point.
Yeah.
If it does lag, it probably only lags by like 4 seconds or something.
Yeah, probably ends up being like a couple centimeters or something, but
because the time it takes light to reach the moon is about 2 seconds, I believe. But that might be the round trip. I'm not sure.
That is round trip, yeah.
Yeah, so 2 seconds round trip, and if it's like 4 times as far away as the moon, It's 4 seconds about.
Mm-hmm. Don asks, why does neutral hydrogen block all radiation shorter than 912 angstroms, that Lyman edge? So you have selective absorption by atoms, but why does hydrogen have this like big band?
Yeah, it's because you can basically at that point, every photon that has that energy is going to be enough to basically be absorbed by the atom and eject the electron. So it means that you only need a very small amount of hydrogen, and you're going to absorb every ultraviolet photon that comes along by that point.
Would that feature block out other, like as you're looking at the early universe, would that Lyman edge block other molecular or atomic features that you'd otherwise be interested in?
Yeah. I mean, there's a lot of stuff short-ordered there, a lot of ionization lines, and you basically, you can't see any of those in these kind of features when we get into the early universe.
Okay. Let's see.
Hey, I wanted to mention something interesting about James Webb. This is sort of the sort of thing I like to find on Wikipedia. So we were talking about how long it took to develop. The very first thing on the table of the planned launch for the JWST, the year 1997, it was a budget of $0.5 billion. And then the table is a really long list of years, and it finally gets to the year 2019, which is the planned launch, is then March 2021 with a budget of $9.66 billion US dollars. So I thought that was kind of interesting about how kind of bloated it got over time and all the delays.
Yeah.
I mean, largely the cost increases with the time because people are working on the mission and they keep getting employed and they keep working, and there's thousands of people who have worked on this.
Yeah. Jonathan, if you could do an experiment on the James Webb Telescope, what would you like to do?
It's a good question. I would probably want to look for biosignatures in the atmospheres of exoplanets.
Yeah.
Or even technosignatures.
Yeah, that'd be really cool. That is one of the James Webb's goals, is to look at the...
Or algae.
Yeah, so if we saw that in another planet's atmosphere, that would be a biosignature.
Mm-hmm. Because oxygen is very reactive.
Mm-hmm. I have a question for Matt. For these intermediate mass black holes, I know with LIGO, we've seen mergers of some black holes of like 30 or so solar masses. Are these the sorts that you're looking for, or are you looking for like larger ones in these dwarf galaxies?
Yeah, no, that's a really great question. So LIGO has detected technically an intermediate mass black hole. However, the after the merger event, this so-called intermediate mass black hole was, I believe, it was 142 solar masses, which is very much at the lower kind of edge of what we would consider to be an intermediate mass black hole. So the community hasn't really taken that as kind of a smoking gun, like, oh yeah, these things are real. So really the ones we're looking for are still a factor of at least 10 more massive than the most massive ones that LIGO has detected so far. But even then, we're not going to be sensitive to, say, like 1,000 solar mass. We're really going to be sensitive to, like, I would say minimum 50,000 to 100,000 solar mass. But that alone would be a big result in the IMBH world.
Okay. And do you expect those intermediate mass black holes to come from mergers like the ones we've seen in LIGO, where you're building it up from like smaller stellar or low intermediate mass black holes?
Yeah, I mean that's the $10 billion question. Is how these things really do form. Part of those kind of competing seed ideas is that if these initial seeds are essentially on the order of intermediate mass black holes, then if they're starting from that mass and then they just accrete from there, then we shouldn't expect to see any. Because they've all grown out of the intermediate mass regime. Meanwhile, stellar mass black holes, we haven't seen any evidence where they really merge fast enough and common enough to grow into this regime. Whereas if you're starting from that low mass seed, then you're going to grow through the intermediate mass black hole. But if these are in dwarf galaxies that don't interact and don't feed the black hole anymore, then you can essentially cut that growth off. And those are the kind of objects that we're really looking for. I don't know if that answers the question, but
yeah. And just to follow up on that, like, do you know if LIGO would be sensitive to the types of mergers that would create these sort of 50,000 mass solar mass black holes?
Yeah, that's another good question. I really don't know. This is going to be a function of redshift, as when they're merging. If they're merging early on in the universe, this is going to make it harder. So given all the factors, I don't think I can really answer that.
Fair enough. Let's see. Don asks, the Hubble Space Telescope had an impressive public outreach component. Can we expect something similar or better for JWST? I think Dennis's video shows they're working on that.
Yep. Yeah, I think you can expect something very similar to what we've seen with Hubble. Certainly, there's a lot of activity at the moment in the communications departments at NASA, the European Space Agency, and the Canadian Space Agency, in terms of trying to get people excited about the mission. And then when we get the first observations coming next summer, it's going to be a very exciting time, and I think we'll see a lot of effort going to outreach and also education.
Fantastic. All right.
I have a question about the JWST, actually. Are there any plans for imaging solar system targets?
Yes, there are. Obviously, we can't point inwards, so Mercury and Venus are out at L2 because we can't look anywhere near the sun. But the rest are all available. And actually, one of the key features of the fine guidance sensor that was developed in Canada is that we can track moving objects within our solar system. Because obviously, the guide stars then will move if you're going to keep the solar system object fixed on the detector. So we have a special mode on the guidance system where we can track a star as it moves across the field of view instead of trying to keep that star fixed in the field of view. And with that, we can observe even things in Mars's distance. So Mars's moons. We can also observe Mars as well itself, although in some of the instruments it saturates the detectors because it's so bright. So there is quite a plan for doing lots of things in the solar system, both the planets and their moons, and then also the more minor objects like Kuiper Belt objects. And I think next month, if Wes is talking to you, he's going to talk to you about his program to observe Kuiper Belt objects in our solar system.
Very cool. Does the fine guidance sensor, I'm just curious, if it's using a fairly wide field for tracking, are there any plans to use it for detection of new solar system objects? Is it sensitive enough to detect things like asteroids and that sort of thing on its own?
There's no plan to use it at the moment as a science instrument. It could be used as a science instrument, but its capabilities aren't a whole lot different to what you can do with NIRISS or with NIRCam. In terms of the field of view is the same as NIRCam and twice that of NIRISS. And then there's no filters on it, so you basically it basically observes all the wavelengths at once instead of having filters. So it potentially could be used. Similarly, NIRISS could be used
Right.
In NearCam's place for if NearCam failed, then it could be the main imaging detector. So there's a bit of redundancy, and different things can be changed if needed. But right now, the FGS is not going to be used as a science instrument at all.
Right.
Part of the problem is, I mean, it'd be nice if you could operate all the instruments at once and download all the data, because that would be the most efficient. But we just don't have the bandwidth to be able to do that. So we're restricted in only being able to download, from maximum of 2 instruments, plus running the guider as a guider the whole time.
And I imagine the processing capability on the telescope itself is fairly limited, so you can't do a lot of data reduction on board.
That's right. We do some simple averaging in time of some of the data, but that's about it. And then the guider obviously has to do all its own calculations to get the pointing accurate. But yeah, we can't really do much processing.
That's fair. David asks, does the telescope use a PhD2 for guiding? And if it does, maybe you could tell us a bit about what that means.
Yeah, maybe. Jonathan, do you want to tell us what PhD2 is? Because I don't know.
Yeah, PhD2 is a program that astrophotographers use for auto guiding for their exposures.
So it's not just 2 postdocs.
Yeah. No, it doesn't use that. It uses some custom software that's designed to work on these infrared detectors with a very fast readout. And we're basically just looking at a very small part of the image, because we can't process the whole image and detect the position of the star very quickly. So we just put a little box around where the star is, and then very rapidly just read out that part of the detector and measure the centroid of the star in there. Okay.
And I guess the astronomers who are going to be using JWST are going to be very relieved that none of the Starlink satellites are going across its field of view.
Yes, yeah, it's given the things that are happening in low Earth orbit these days, I think it's very good that we're not going to be there. And as soon as we launch and get away from the Earth, we should be clear for a while.
Mm-hmm. Will the Canada Data Center here in Victoria keep data for JWST as it does for Hubble?
Yes, it will. Yes, we will be getting all the data as it becomes public, and storing it and serving it to any users that want to use it. And we're also working on a cloud-based science processing software platform for JWST users. That is going to make life a bit easier for Canadian JWST users who want to process their data. We'll have machines, virtual machines, kind of set up already with all the right software they need to be able to process it.
Fantastic.
Chris, I have a question for Chris. Is there any citizen science projects that you know of or being thought of for James Webb?
No, that's a good question. I haven't heard of any, but obviously, there will be an archive and there will be a lot of data that becomes public quite early on. So I can imagine there will be some citizen science projects, but I haven't heard of any so far.
Okay, thanks.
All right, unless any, sorry, my cat just threw a box down the stairs. Unless there are any further questions coming in from YouTube, I think that's all the questions we've got for our astronomers today.
I have one other question for Chris. Have they checked to make sure no cat has snuck into the spacecraft before launch?
I'm pretty sure they'll do a thorough cat check now. There is actually there's a cover on the entrance from the secondary mirror to the tertiary mirror that's been covered kind of all this time, because we don't want dust and contaminants to get in. And there's a big sticker on the front that says "Remove before flight." So we're hoping that somebody does remember to take that off when they see that, when they're doing the final packing, because if that cover stays there, then we don't see anything.
That would be a very rough point of failure. All right.
Okay, Dennis, is there something about a cat being in somewhere? Is that it?
Cats are well known for getting into places that uses. So it's just
okay. I just didn't know whether there had been something in the past.
No, not that. No.
Oh my gosh. Okay.
No, not that I know of. But just cats are well known for just getting into all sorts of weird places. So,
Yeah.
and then Aaron's cat brought that to mind. So, anyways.
All right. Don says it's not a catadioptric telescope. All right. So with that, thank you so much to Jonathan and Chris and Matt for answering everyone's questions. We're going to move along to our electronically assisted astronomy. We've got David Lee and some other folks who are eager to share their latest round of images that they've processed.
Well, good evening, everybody. Certainly very exciting news to have a new instrument out in space. I wish we had something like that down here. Maybe we could initiate something here. But we have a couple of images, or quite a number of images tonight. Now, we haven't been blessed with great weather recently, but I think some of the folks from the EA group have managed to pull a few things together. And I think Dan Posey is with us tonight, and I think he's going to show us a few things that have been captured on the Plaskett. So Dan's with us tonight. The usual suspects, David Payne's with us, and also Brock Johnson. So I don't know where we want to start. Brock, I remember you saying that you had an image with M31 with taken through an HA filter, which is interesting because of the different kind of wavelengths of discovery that we've seen even tonight. Why don't you take over the screen and show us?
Sure. I'll start by showing one of just a visual of M31, the Andromeda Galaxy. Can you guys see that?
Yes.
So this is one that's just taken with just full-on RGB, no filters, just to get as close as possible to what it would probably look like with our eyes. But I wanted to do one that would just give me a better sense of where in Andromeda there are star-forming regions. And generally in star-forming regions, you'll find that there's a lot of gas, a lot of hydrogen gas, and if there's young stars that are just coming to life, they're often making that hydrogen gas glow, and it glows in a very red color. So just a few nights ago, we actually had a clear night, and I set up my telescope and I shot Andromeda with the filter for HA, hydrogen alpha, and oxygen, and got quite a few hours on it. And this is actually the result that I got. So this shows, this is just in two very narrow band colors. The sort of cyan color is from the oxygen, and then the red is from the hydrogen gas emissions. And it's quite strikingly different from the full color version, but it's quite interesting because you can really see how much area within the Andromeda Galaxy has these nice red blotchy bits. And these are, of course, are the nebula, the things like, when we actually look at, in our own galaxy at things like this, somewhere in Andromeda, there's probably someone on a star over here pointing his telescope at this one, and they probably made up some crazy name for it. And, it's amazing that there's quite a lot of that going on there.
So Brock, you mentioned this was through a specific wavelength. It's actually two wavelengths we're looking through here.
Yeah, this is the oxygen 3 band, and the hydrogen alpha. The hydrogen alpha is the red, which is I think 670 or something. I don't remember how many nanometers hydrogen alpha is. But it's a deep red, and it's primarily associated with, hydrogen is the most abundant gas in the universe, but when it's surrounding young stars, it starts to glow because they're emitting tons of, ultraviolet and other high energy light that excites the hydrogen, and then it re-emits quite a lot in that one particular band. Hydrogen emits in quite a few bands, but that's one that we can visibly, see with our own eyes. So it's a common one for astrophotographers to try to pick up on.
Yeah, so the first image you showed us was more of a visual band.
Yeah, this one is visual.
Mhm.
And if you look really close, you can see a few little red blotches. And I haven't had much time with this data, and I've been trying to, my goal is to kind of overlay some of this extra color onto the other image without screwing up the other one too badly. See if I can, but add a little bit of pop. But also it was interesting just to try to pull out where that's actually happening.
Yeah, it's quite interesting that amateurs have had access to some of these filters for, well, quite a number of years now, but it allows us to explore things in specific wavelengths, just like JWST is going to be looking in infrared. We can look in different wavelengths as well.
Yeah.
Brock, that image really pulls out the 3D. It looks very 3D, and you can kind of see how it kind of curve. There's a curve in it, or to me there is. I mean, maybe it's not there, but to me there's a real curve and a dip.
Yeah, I agree. I see that as well, and I saw that actually. Dan Posey posted an image. It was quite a wide field shot that had a bunch of what's the stuff called again? Anyways, it was a beautiful shot, but it showed a lot more of the extended features of the galaxy. And you could actually see quite a bit of an S curve. It kind of tips up here and kind of curves down there. And you don't see it in a lot of the shots of the galaxy for some reason, but it shows up in this one.
I think it's even more apparent because in many shots of M31, it tends to be a bit of a monochromatic image.
Yeah.
So with the use of the narrowband, that extra layer of color difference makes it 3D automatically, actually, in a way.
I think the warp on Andromeda is due to interaction from the Triangulum galaxy. That's the little one. Oh no, Triangulum's not in this field. That's one of the dwarf galaxies I'm looking at.
Yeah. Yeah, Triangulum is close, but it'd have to be quite a bit wider to catch Triangulum. But they're not that far away, and they're both part of the local group.
Yeah, that's very nice. You often see the traditional image. M31 is often one of the first deep sky objects that imagers try when they're just starting out. But the variation of this theme has been vast since narrowband has arrived.
Yeah.
I just want to go back to calling M33 or the Triangulum little. I know it's not quite as heavy as the Milky Way or Andromeda, but I don't think I've ever heard it called little before.
Did I say that? Or?
No, Aaron did.
Aaron said it was little.
No, sorry. I was going to point out the little dwarf galaxy just below Andromeda in the image, but then I remembered that's a dwarf orbiting Andromeda, not actually the Triangulum.
It's the companion that everybody talks about. I think it's M32.
That or 110. There are two.
Or 110.
Yeah.
I can never remember the difference. The other one that's that bright object to near the top is an associated galaxy as well.
The Triangulum actually has a lot of hydrogen alpha regions, even without using a filter. It stands out just even in a visual image, much more than it does in taking a picture of M31.
So, yeah, very nice.
Andromeda is one of the quieter galaxies.
Yeah. And actually, I also, that same night, I started out because I wanted to catch the Rosette Nebula, but it wasn't up high enough until 1 a.m. before it got above the trees, and it was quite low in the sky. So I started out with the sequence set up so that I could get Andromeda, and then once the Rosette was high enough, I switched targets. But it's actually, without even planning it, I kind of got that nice shot of Andromeda showing those star forming regions. And then of course, this is a star forming region. So this is a close up of one of our galaxy's star forming regions. And you can see in the center, there's an open cluster which is NGC 2244. And it actually has a small number of very young stars that are basically making this surrounding hydrogen gas glow in a beautiful rose-shaped form, and it's quite a nice shot. I haven't really had much time to process this one, so I also only have 22 subs, but I quickly threw something together for this just so I can speak to it a little bit.
Brock, you're using one of the newer sensors that have been available to us, aren't you?
Yeah, this is a reasonably new astro camera with a Sony sensor in it, the back contact ones.
Yeah, I've been totally just floored by the level of dynamic range these new sensors have. Actually, they're far superior to what we've been able to do in the past.
Yeah, considering this is such a small amount of data, like it's less than 2 hours of data, the quality of the image actually is pretty outstanding. Like I want to get probably upwards of 8 hours on this over the next, probably taking 3 months.
Yeah.
And I probably also want to capture some Orion stuff, but
yeah,
I think
this is great. At least here on Earth, our technology is constantly evolving. It's not capped at all. We always get fresh presents every few years.
Mm-hmm.
Hey, Dave, do you have anything to show us tonight?
Sure, I could show you a couple of things. I actually put together a couple of images of star clusters. So this is what results from I did that too early. I have to back up and share my screen. So this is the first of two clusters I want to show you. And these two clusters have, well, there's two on this one frame. There'll be one on another image I will show you in a second. They highlight another part of spectral analysis, but this time dealing with thermal photons rather than atomic spectra. And this involves looking at the kind of light that stars emit and determine how old they are and how hot they are and even how fast they are moving perhaps towards us or away from us. So the two clusters I'm going to show, the first one is a double cluster. It has a lot in common with the second cluster I'm going to show in a second. This first one is known as the double cluster in Perseus, and these two very bright clusters, you see, they probably came from either the same star forming region or two that were fairly close to each other. They're about 7,000 light years away, and they're about 100 light years apart between the two. What is characteristic of this star cluster is that these stars you see are mainly bright white, blue-white, and they're of a spectral class B0, which are basically the hottest blue stars that you can find. To add to that, they're also blue shifted somewhat because they're heading towards us at about 20-ish kilometers per second. So they're moving actually towards us at quite a high speed. Why are they so bright and white and hot? It's because they are very, very young. This is a very, very young star cluster. And young in these terms means only about 3 to 6 million years old. So I believe you're going to see one of Pleiades to give you an idea that the Pleiades, which is also a young star cluster, but it is 20 to 40 times older than these two clusters. But like very bright stars, they shine brightest, but not for too long. So the second cluster I'm going to show is about
Oh,
the
Dave,
same.
Dave, before you leave this, can you
Yeah.
tell us anything about the red stars, the cooler stars?
The red stars are generally not part of the cluster.
Okay.
They're either in front or behind the main cluster. I think this is before them, but the stars are all only approximately the same age. You will get some older stars in there, but generally the stars that are members are quite large. To give you a sense of how big these stars are, if you put the sun in amongst them, it would be one of the dimmest stars you see in this image. So they basically put our sun to shame largely in terms of their size and their brightness. But bright stars don't last very long. And so the second image I'm going to show you is of a different star cluster. Now this, as I said before, well, just a few words about this one. It's about the same size. It's very close. The previous image was in constellation Perseus. This one's in Cassiopeia, and they're so they're fairly close to each other. And a lot of the stars are part of the Milky Way that we see. And it's actually hard in this term to determine, hard in this image to determine what stars are part of the cluster and what are outside of the cluster. But one thing that is striking in comparison, these stars are also very giant stars, taken with the same, roughly the same field of view and everything. But these ones have a very pinkish hue to them compared to the other. And that's largely because, and this star cluster is about the same distance away. The other one was 7,000 light years, is about 8,000 light years. What's different is instead of being 3 to 6 million years old, these stars are 1.6 billion years old. So they're not quite 100 times older, but they're basically the same stars. But that's what happens to very large, very bright stars, is they don't have legs to last a long time. Just for comparison, our sun, which is nowhere near as massive and as bright as these, is, I think it's 5.5 billion years old or 7.5 billion years old. So the sun has much more legs than these stars. But you can tell this from basically the color. You can tell the temperature of the stars and then surmise its age from the color that they burn. These stars have burned most of their hydrogen and are now classified as giant red stars or giant yellow stars rather than the blue stars in the other image. So it's interesting using color, and these have been photometrically calibrated against Gaia data. So it's interesting to use color to surmise a lot about the star fields you see.
Very nice. Okay, thanks, Dave.
Thanks.
Dan, I think you have some stuff to show us from the Plaskett.
Yeah, just the one image from the Plaskett tonight.
Okay.
But it's always nice to be able to share a result from it, and just give me a second here. All right. So over here on the left, we have a shot that we captured on the Plaskett back in October. We were lucky enough to have a night on it, and it was a night filled with some challenges, but this was one of the earlier results I managed to get out of it on something called the Nautilus Galaxy. So again, thinking about that ability to look at a feature in the night sky that wouldn't immediately be available. Back when the telescope was created, we did this in about an hour of data, give or take. And there's some quite interesting background galaxies that are dotting the frame. These aren't stars, these are background galaxies, as well as a fairly deep look at attached material coming off this galaxy. It's likely been churned up and disturbed by this companion here, I believe.
So Dan, would this be visible on an amateur scope, or does it demand the plastic?
It's visible. It's borderline. The Nautilus galaxy is not exactly bright, which is part of why, if we're going to go hunting with a cannon like the Plasket, where it has quite a bit of reach, then this was something that was quite nice to go after for the evening. I mentioned there were some difficulties that night. The mirror was just about to go out of the telescope to be recoded, and so I think that we shared a video of that recently, or there might be one available. But that process means that the floor is open, and one thing that you'll probably know is that astronomers don't love light, particularly light that's not coming from somewhere very far away and is typically quite a bit older than we are. And so on that case, the other filters have been a little bit polluted by the light coming through the hole in the floor, where I think an exit sign was shining on us. So I was able to salvage the green filter. I'm still working on the other two.
Okay.
And then a couple quick examples of what you can do with an amateur telescope. So I have shot this with an amateur one. It just, you can't go nearly so deep so quickly. That's the difference. I would probably need between 5 and 8 hours to get this amount of depth, not one. And you hit your ceiling much faster in terms of that point of diminishing returns, where adding more data isn't going to necessarily net you a better result or a better outcome. For not to make it too technical, but generally the way that it works for digital versus using a photographic plate is that you can increase the signal in your stack by the square root of the number of the frames that you have in your stack. And the increase in signal then gets the most aggressive ramp up on the early end of that, because it takes more and more and more and more to keep improving as you go along. And so professional telescopes tend to have far longer legs, to use Dave's words, at the beginning of the process than you do in an amateur scope. It's not that you can't try and get there if you have enough time with any equipment. This is one that was shot with an amateur telescope, though. This was shot with a little 14-inch from our club site in Victoria, and I thought it was just a good example to chat a little bit about tonight, to give an idea of what is possible and where there's so much excitement for these new incredible instruments that are coming our way, to be able to dig deeper and to look into galaxy clusters like this and get a better understanding of how all this material fits together. So in terms of scale, I think the Nautilus galaxy is about 300-ish million light years away. I'd have to go back. I didn't cite that before I came. This cluster is just around, let me see if I noted this down, actually. Give me a second here.
It's very Hubble Deep Field Romanesque.
Sorry. I just wanted to check if I noted it. I didn't. So it's 1656. I have a feeling that it's about 400 million light years away. So still reasonably close, but the deepest that we've punched out from our own little site was just around 2.3 billion light years. And this, you get quite a bit more detail in it because it's a bit closer. And then the final image I thought I'd share tonight, Brock, when you mentioned it, I did pull up that frame. This is the one that Brock had mentioned on M31 that has that little bit of an S curve in there. And the other feature that he had mentioned that was in this frame is something called integrated flux nebula. So deep background structure and detail that you can sometimes see between galaxies. So it's associated with our own galaxy, but it's not illuminated by anything particular in our galaxy. It's material that's only illuminated by the aggregate light of the Milky Way, or the integrated flux of the Milky Way. So it's incredibly faint. This is about between 1 and 10,000 times fainter than this on the kind end of the stick. It's around meg 25, and even the surface brightness of this is around I think meg 17 or 18.
So Dan, how many hours of exposure is that?
That wasn't too much. I think this is only a couple hours, but I was using a trick to do it, which I had mentioned earlier, which was a very fast lens or
is this the 105?
Yeah. So a very aggressive ratio between how wide the lens is and how long the lens is. And so if you think of that being like a bucket of water, it doesn't take too much rain to fill up a fairly shallow but broad, I don't know, bucket lid or something similar to that. It'll be overflowing quite quickly. If you think about, instead of rain, that being data that you want to receive from the target, I was able to use that trick in this case. And so that brought my exposure subframe time down to only 30 seconds, but then I took a few hundred of them. So that's where you need a lot with amateur equipment to try and do anything like what a professional telescope can do. And so in this case, the trick was just to trade off the resolution, where unlike Brock's image, this falls apart if you zoom in. Brock has much richer detail, but I have a much wider view, which allowed these features to come out. And on that, just another thought, because there's always a different way of looking at familiar things. And so it's Pleiades season again, it's back up in the sky. This is definitely something I would call an overcooked image, but I overcooked it for a purpose, which was to show how much is going on out there, where we all like to think of deep sky images as being with this perfectly black background, and that's not always the case. So this is one within our own galaxy, but instruments like the James Webb, and certainly what Hubble's done with the deep fields, is be able to show you that if you train enough time on any area of the sky, there's a bunch of really rich detail that doesn't pop out right away. And in this case, what I was trying to look at was not just how much dust and what those features looked like in the area, but how the bright blues of the Pleiades star cluster, which are young B-type stars, again, tying into what David mentioned about different star classes and ages, reflecting off the different nebula and background dust around here, you get this rich, vibrant blue. But then you can see that if you look around the region, there's a lot more material there that all has its own different color and character to it. So sorry if somebody else is going to talk on the Pleiades. I don't want to spend too much time going down that path. So I will.
No, I don't think anybody else is showing anything. I make the whole concept of the new telescope and the kind of stuff that we're starting to see with narrowband really has me intrigued, because it's really going to allow us to reinterpret classic objects. Because I mean, we know what a lot of these objects look like from maybe 20, well, maybe even a century's worth of imaging these things, but they will become new in a sense when we try to reinterpret them through different bands.
Yeah, and different equipment gives you a new way of looking at the world. I wasn't ever able to do anything even in the realm of this before acquiring the equipment that let me do it. And then it seemed like the most entertaining thing to do for every shot was to try and chase background dust, which you have to be careful, because even though it's fun to show that space can be a dirty place, I seem to get some pushback for ruining the idea of this pristine environment out there. That and I had to stop for a while. I was told that it was tempting for people to pull out a vacuum if I went too much farther down that path. So
I was going to say, you got to make sure you wipe down your lens first.
Yeah, I swear this isn't just I didn't just store it in a dusty closet and then try and pass it off as a photo for all of you. It's actually up there. But
I wanted to pop in and say point out one thing about the Pleiades. If you
please
let me. So one thing to contrast it with the Rosette Nebula and the star forming regions that we saw in Andromeda. The Pleiades is one of these young star clusters, like the double cluster we saw in Perseus, but it does have gas around it, which in a normal young star cluster, you'd see reds in the gas from this hydrogen alpha as the new stars ionize the gas around them. The Pleiades is quite distinct in that it has mostly blue, and this is because this isn't the original gas cloud that the Pleiades formed in. It actually formed, blew away the gas around it, and then as a cluster moved around the galaxy for another 20 or so million years and happened to find itself in a new cloud of gas, and it's lighting that up. It hasn't had time to heat the gas yet, which is the main thing that's causing the different color. Whereas the red color comes from ionized hydrogen, hot hydrogen around these stars. The blue is actually coming from Rayleigh scattering, which is the same type of scattering of light that is why our sky is blue, scattering light from the sun. So what you're seeing is the blue light from these stars being scattered. But if we watch the Pleiades in this cloud of gas for another few million years or so, then you'd start to see a lot more red, especially around these big blue stars. So we're catching it just sort of as it's entering this new cloud of gas.
That's a wonderful insight, Aaron. I never thought of it that way, but you're right. The time domain is so vast here that we forget that these objects have many lives, I guess. They've lived in lots of different places. Yeah. I think that's what you're pointing out. I never thought about that, but you're right.
Well,
Aaron,
go ahead.
Sorry, it's Don. I actually always thought that this was actually reflection off of the dust itself, and therefore this particular photo would actually be really illustrative of the dust in the environment. But I could be wrong. But
so this type of nebula is called a reflection nebula. In the sense that it's just reflecting light, or scattering light. It's not generating its own light.
I understand that, but it's not. It's reflecting off of the dust as opposed to. Okay. Yeah.
Yeah. The process of that reflection is the Rayleigh scattering.
Is it? Okay. Okay.
Yeah. As opposed to scattering in a sense by ionizing hydrogen and then having the hydrogen recombine, and that's causing the hydrogen alpha. With the Rayleigh scattering, it's like it hits and bounces off right away. With the ionization, it hits, breaks apart the hydrogen, and then sometime later, that hydrogen finds another electron and emits.
So are you saying this dust is the same size as the molecules in our atmosphere that cause the Rayleigh scattering?
Most of what we're seeing is from like atomic or small molecular species, oxygen or hydrogen. We are probably getting some like direct reflection off of the dust grains as well, depending on how dense they are. But and because the stars are giving off mostly blue light, that's most of what gets reflected back to us. So I think the dominant one is Rayleigh scattering, but I could be wrong there.
Well, let's look into it. I mean, it's an interesting thing. I mean, I didn't realize you could get blue from both. I mean, that type of blue light that we see from oxygen in our sky could also be Rayleigh scattering in interstellar objects. But that's interesting.
I'm just Googling the definition, and it's basically a reflection nebula, not hot enough to ionize the cloud's hydrogen. Dust reflects the light. I could be wrong, but I'm almost certain that Rayleigh scattering is a significant part of it.
I can actually show an example of why reflection nebula are so interesting, and the example I'm going to use is this Plaskett shot, because I've used it to cheat my way around the filters with the Plaskett. So often when we're imaging on the Plaskett for amateur imaging nights, we're using a professional photometric filter set called the Sloan Digital Sky Survey filters. So they go UGRIZ, so UGRIZ, U being blue/ultraviolet, G being right in that green-orange band, R being quite red, and then I and Z being very, very near infrared, and then just bluntly into the infrared range. The problem is that at our altitude, when we're using the Plaskett, the U filter is essentially useless. It captures very, very little. There's almost nothing getting through. And you need 3 filters usually to create color. You can do it with 2 using a synthetic channel in the middle, but it doesn't work as well as using 3. And so I had to pick out some objects that we were going to shoot for a night, because Unfortunately, if you take a picture of an emission nebula with that filter set, you wind up with it being lime green, because once you map green to blue and the red filter to green, all you're left with is the eye filter to populate the red channel. And let me tell you, it cannot compete with hydrogen alpha emission, so you lose. But in this case, reflection nebula, because they're reflecting the light off of the illuminating star, they act like black body emitters, meaning that you're able to take a picture of a reflection nebula and then map it back to a proper RGB black body spectrum when you're mapping it. So it will go from being this, so instead of an emission where you only have very particular bright lines, you wind up with the rainbow, and you can shift the entire color spectrum of that rainbow a little bit left to get over into the proper RBG or BGR range. So I did that here. So I do know that at least in some cases you're able to fully recover, but I don't know whether the cause or the origin will be Rayleigh scattering or something else in this case. It does tend to match up, and you can see this here if I actually get off my rear end and zoom in. It does tend to match up reasonably well with the parent stars that are creating the light and then emitting it out. And just to give everybody in the audience context for one last thing, and then I'll go away. This is, I think, a shot of the Pleiades I took reasonably recently. And this is to give an idea of what we typically look at when you look at the cluster with an ordinary amateur shot. And so if you look at things like these features here, you can already see the color begins to shift relative to the main reflection here. And you begin to see a few of the background dust features coming in, but not too many. For context of how different this view is, that's that dust feature I just picked out. And it's very well inside the outside borders, and all of that dust where you could see the color shift in the other shot is still quite blue. You don't only really get the transition out much farther out, where you go into the more ruddy red kind of chocolate muddy color that you get with a lot of interstellar dust. So again, new perspectives for old friends when you're looking at targets that you shot for the better part of a decade or two.
So yeah, every reference I'm finding here agrees with you. Actually, it's Rayleigh scattering, but I just assumed it was related more to the blue color of the star. So
it's a bit of both. So the Rayleigh scattering, so it works for both molecular species and dust grains up to the size of a few nanometers, because it just has to be smaller than the wavelength of the light. And then the efficiency is also very heavily weighted to the blue. So when you have an already blue star in a nebula full of the dust and gas, it just blasts back the blue to you, but and not as much of the red. So if it was super dusty, like if it had a lot of like larger dust grains and stuff like you see in a protoplanetary nebula, then I'd imagine you get more of the red because that would be directly reflected off of it. But the Rayleigh scattering, I think, is the mechanism for most of that light bouncing back.
It's super interesting because I guess I just never really thought of a lot of the dust as being as tiny as air molecules.
It isn't. Air molecules are much smaller. But like both of them are significantly smaller than the wavelength of blue light. So like,
well, that's pretty small.
400 nanometers.
It's pretty small, though.
It is. But air molecules are much smaller than that.
Or the dusts tend to be.
I think Dan was going to say something.
So unfortunately, I tried to demonstrate Rayleigh scattering with this green laser pointer I have, but my laptop webcam is not sensitive enough to pick up the beam. You just get an unearthly green glow from me. But it's the same mechanism where if you shine a green laser, and if you've ever watched somebody point one of these up in the atmosphere, the beam isn't, it's not reflecting off of smoke or fog or something else like when you use a red laser pointer, like when you were kids and you got the little $5 one at the dollar store and went out there and you could only get it to do something cool on a foggy night. With these, it's what Aaron's discussing, which is Rayleigh scattering, where you're scattering off the molecular structures in the air along the path of the beam, and that's why the green beam jumps out.
Right.
So, yeah, sorry everybody, the drawbacks of remote rather than in person, but it's a good demonstration of it if I'd been able to do it.
Did you just say like the red lasers when you were a kid?
Yeah.
I feel so old.
Why were those newfangled things or something?
Don't say anymore, Don.
No.
Don't say anymore.
No.
I think commercially they only got super available like a couple decades ago.
David, can I ask Jonathan one kind of last question
sure.
that relates between what you guys have been talking about and the James Webb?
Yes.
Jonathan, I think Dan Posey and I think also David, maybe it was Brock, now I can't remember, had some pictures of galaxies, and they gave some I guess how far away those galaxies were. But the James Webb, I mean, one of the main science things that the James Webb is going to do is to go back in time, like farther than we've been pretty well with an awful lot of other telescopes, or I mean, I guess, well, certainly the Hubble, is how much further are they going to go back than what we normally look at as some of the galaxies that we just have taken pictures of even here today? Do you know the difference between that the time or the age?
I don't know the exact difference, but I know it's.
I wish I could remember. I remember seeing in some of their promo stuff, they have a picture of us on Earth, and then images taken even with Hubble, right, that go out to a certain distance, and then they go way down the line. Like, I don't know if it's an order of 10 or what, but it is quite far back.
Yeah.
So Jonathan, how old is or how far away is M is like the Andromeda?
I don't know for certain how far away that is.
Who
else does?
Oh dear, I can't remember. Anybody know offhand?
Well, somebody's Googling it right now.
Light years?
2 million light years, something like that.
Yeah, I think it was originally estimated at
2.5.
1, and then it became 2, and then a bit over 2.
So 2.5, about 2.5.
Yeah, 2.5 million light years.
Million light years. But we're going to go back, I think, in the James Webb to about 11 billion light years, right?
It's not even comparable.
Yeah, I mean, like beyond anything that we kind of have seen.
I wonder if the images are going to be shocking in that sense, because we've never seen anything that old, right?
Yeah.
Or are they just going to be dots?
I don't know.
Well, that
should we take bets?
If we knew now, then it wouldn't be as much fun when we get to see it.
Oh, okay.
If we knew now, we wouldn't need the James Webb.
Yeah, but this is the fun and discovery.
So
we get to find out.
I think there's a little bit of a difference too, in that you have to consider how far back in time we're seeing things at versus the actual distance in light years, because you can see further than like the most distant back in time right now is 13.4 billion light years, I think is the record, and the universe is 13.8 billion years old. But that object is more than 13.4 billion light years away because of the expansion of space-time. It's like 30 some billion light years away, if I'm correct. So I mean, there are things that are much further, but we're not going to see that much further back in time. So there's a distinction there because of the expansion of the universe. So yeah,
it's okay. I'm going to have to think about it, because I always thought kind of basically time and distance were
kind
of
I used
related.
to think that way too, but it's
the
not.
local universe. That's correct.
Sorry, what did you say?
For local stuff, that's correct. Once you out to about like 5 or 8 billion light years, but past that, it diverges pretty quick.
Okay.
Yeah. So this object, I'm just using, of course, the oracle known as Wikipedia right at the moment, but it's 13.4 billion light years back in time, but 32 billion light years away. So
it's
that
the
makes
distinction between how far the light has traveled versus the instantaneous separation between the two objects.
Between the two objects. Okay.
Yeah. It's
because
like
the
if
light was
you're-
emitted when it was much, much closer.
It's like if you're running on one of those moving sidewalks at an airport.
Yes. Yeah.
The distance that you have to travel and the actual distance that you move between point A and point B
Right.
won't
Is
necessarily
different.
match up.
Is
I like
different.
that. That's good. That's a
I'm
good
sure
one.
glad you're here, Jonathan. You
Yeah,
can explain it
yeah.
much better than me. So.
Well,
like coming
I
up
think
with
that's all we
analogies
have,
like
but that
that.
was it was an interesting divergent discussion.
Yes, I didn't I had planned to talk about the Pleiades for 30 seconds, so I appreciate the different pathways we've gone on, but that
Yeah, man, I can digress.
Well, that actually brings us to just over 5 minutes over our planned end time. So this seems like a good spot to wrap
Sure.
up. So I want to thank all of our EAA speakers,
Yeah,
David,
fantastic.
Dan,
Always awesome.
Brock, and David.
Thanks.
Yeah, thanks, guys.
Thank you so
Fabulous.
much. Thanks, Calvin,
Yeah.
for
Exactly.
tech support and running the YouTube. Thanks, Jonathan, for joining us for Ask an Astronomer. And
Yeah.
thank you especially to our two speakers, Chris and Mark,
Matt.
for their
Matt.
Oh, God.
Yeah.
Chris and Matt for their fantastic
Getting
talks.
late.
And we're looking forward to seeing the science that comes out of the James Webb once it makes it up there. Thank you again, everyone, for joining us this evening for our
So our
star
next
party.
star party
Yes.
is the date of the launch. So
Yes.
it's the 18th of December. And so by the time we get online in the evening, we'll either be all going, woohoo, or going, yes, well, maybe
Yeah.
it's been, it hasn't been launched yet. So we'll see what happens with that. But we have two other speakers that are again, kind of local Canadian speakers that are going to be with us. And Madeline Mitchell. Oh my goodness, I hope I have that correct. And and I've just lost oh my goodness. And I even know him. Okay, I'm sorry. Oh dear, I haven't
That's
got
okay,
that
Lori.
sitting right in front of me. And they are also investigators, like doing part of the science and the science cycles. And so they are from from around here and from the NRC. And so we're just so fortunate to have people that are just right here. I mean, this is big news just for Victoria area people who are doing a lot of the work. So we're very fortunate that the James Webb Group, the NASA and the Canadian Space Agency has given us the ability to have these speakers come and join us. So it's going to be wonderful.
And we'll have to start thinking about how to work all this material into school tours and other educational materials.
Right.
Yeah.
Oh gosh, yeah. To get
advantage of
things a little bit more. Anyway,
We'll have to see if we
join
can
us
get a
on the
model.
18th of December. It is also the winter solstice. So
Very close to it, yeah.
Right.
bring light and candles.
Yes.
Okay.
So
Thanks, everybody.
again, yeah, thank you. And be sure to
Good
check
night.
us out at centeroftheuniverse.org. Like and subscribe to us on YouTube and find
Yes.
us on social media at FriendsDAO.
Yeah.
See you all again next month.
Thanks
Yep.
all.
Good
Good
night.
night.
Everybody.
Night.
Everyone, good night.